we're going to get started. Welcome to the Harnessing Machine Learning Cross-Working Group. We have a lot of awesome talks today. Each speaker has about 15 minutes, which is their talk and questions. At the end of the first half, we do have ample time for discussion. So if you don't get to ask your question after the talk, feel free to save it for then. If you're online, please use Slido to ask questions, and if you're in person, please walk up to the microphone to ask questions. I think that's it. And we'll have our first speaker, Aman.
Oh, wait. It's just this. Okay. Hi, good morning, everyone. First things first, let me get the title straight. Sorry, that was too generic. I am Aman Gupta, and I'm a research scientist at Stanford University, and today I'm going to discuss our results from the newly developed deep learning parameterization for representation of atmospheric gravity waves in climate models. And so I guess I don't need to go through this slide in great detail, but essentially most of us might have encountered gravity waves in literature, or may have even encountered them in daily life. Essentially, they are fast-scale linear perturbations to a stably stratified atmosphere, which could be caused due to convection or uh-oh. Is there a pointer? It doesn't work. Oh, okay, thank you. And these waves could be generated around strong thunderstorms, internal disturbances of a stable atmospheric layer, or even flow over mountains. Now, a typical life cycle of a gravity wave is, generated. This a wave packet is generated through a myriad of sources, and then it predominantly propagates in the vertical and grows in amplitude, encounters critical levels and breaks, and drives the flow. Now, the representation of these waves in climate models have notable biases. So if we quickly look at this animation here, you'll notice a couple of things. These waves are generated over Andes, the Andean topography, but then they propagate, the wave packet propagates significantly, leaves waves. And as they move away from the source, they experience a change in wave number and orientation, and refraction in the wave. And then there's a temporal coherence to the packet, right? So these are the key properties that you would want a parameterization to represent in climate models. But then if you simply look at this wave again, sorry, I'm not able to figure out the pointer. But then for this given gravity wave phase structure, you would, if you explicitly compute the resolved fluxes, it would look something like this, but then a typical parameterization would give you a drag profile or a flux profile that looks something like this, disjoint, right? So there's barely any variability over the Southern Ocean, which would what you would expect. And neglect of these properties leads to several biases. In the middle atmosphere, for example, erroneous QBO representation, delayed polar vortex breakdown in the austral summer stratosphere, even biases in the jet strength and the meridional overturning circulation in the mesosphere. And so in this work, what we essentially do is we create a deep learning parameterization which learns from high resolution observations the flux evolution of gravity waves, and then embeds, and then this scheme can be coupled to a dynamical core or an atmospheric model to then sort of substitute for the parameterization. And so the hope is that it can learn all the physics, all the prominent physical properties of gravity waves in the atmosphere, thus representing gravity wave effects with more fidelity. And so very simply what we do is we try to create a mapping between the background atmosphere, the background dynamical conditions, and the subgrid scale fluxes that the model, a coarse model, would usually miss. So we use ERA5 data, ERA5 reanalyses to compute the compute the fields. We coarse grain these fields, winds, temperature, horizontal winds, vertical wind, and potential temperature on from a 25-kilometer grid to a 280-kilometer grid, which is what a typical climate resolution would be. And then corresponding to that, we compute the subgrid scale fluxes. The direction flux is shown here, U prime, omega prime, V prime, omega prime. And then we, again, coarse grain them from a 25-kilometer grid to a 280-kilometer grid. And so we create this mapping where the input of the model is these coarse grained conditions, and the output of the model are the directional fluxes, the subgrid scale variability. And so we train a set of 3 models, sort of representing different degrees of non-locality. The first one, model M1, as I call it, is simply inspired from traditional parameterizations. You give it one column of data, like one column of input background field, and then it predicts the flux in that single column. The second model, M2, has slightly non-local, slight non-locality associated with it, where instead of one column, we give it 9 columns. So 1 central column plus 8 neighboring columns worth of input field, and then it predicts the flux in that central column. So more information to predict the flux in the same column. And then on the other hand of the spectrum is this fully globally non-local model, where we throw in all the information we have over all longitudes, latitudes, and pressure levels, and then we use a convolutional neural net to predict fluxes over all the latitude, longitudes. So it's like a one-shot prediction for the whole atmosphere. And again, we train it on 4 years of ERA5 data first, and then because ERA5 does not resolve the whole gravity wave spectrum, at least in the mesoscales, we complement it with 4 months of fluxes computed from a 1.4 kilometer IFS model from ECMWF. And we evaluate it on 3 key statistics. First is simply, how it performs in time, in real time. Like, what's the temporal evolution? Does it get the temporal coherence correct? Second is the seasonal averages. Does it get the seasonally averaged flux distribution correct? And the third is a histogram, just to look at the range of values the scheme can predict. I would quickly run through the results. I mean, looking at the first test, we look at 6 well-known gravity wave hotspots, both orographic, non-orographic. And what we notice, if you start from the mid-latitudes here, is that the 3 models compared to ERA5, like the predictions from the 3 models match pretty well with ERA5 in the mid-latitudes. We quantify it using the Pearson correlation coefficient, and they are pretty high, almost indistinguishable between the models. But then the problem is that the tropics have much lower correlation coefficients. If you look at the values, I hope they are visible. The single column model performs the poorest, and the most non-local model performs, provides the most accurate predictions. And so just to focus on the Drake passage again and kind of give a flavor of what the scheme is, predicting, like the horizontal structure of the fluxes. And you see that there's a clear, the scheme is clearly learning this horizontal propagation of the fluxes away from the topography. It's identifying the sources well, like the Andes, the Antarctic Peninsula, certain sources along the Southern Ocean. And then it's also, basically we get a coherent profile of the fluxes that match pretty well with the underlying training data. And similarly for seasonal averages, we look at the JJA June-July average mean this is the ERA5 fluxes, and then these are the differences. So the 2 models, M1 and M2, that are single column and slightly non-local, they give reasonable predictions in terms of, predicting the mean climatology, but then there's these notable biases around, notable errors around the steep Andean topography. But then those biases are again alleviated when they're not there for the predictions made by M3, with a caveat that there's certain introduction of the biases in the tropics. So that's okay. I mean, I'll discuss more later. And then the third test is just looking at the histograms of the fluxes, global fluxes predicted by these models. The left column shows the mean, the histogram of the means, and we see that there's a strong agreement between between ERA5 and all the 3 models. So in a mean sense, they get the range pretty well. But then if you look at the daily samples, that sort of brings out a sort of a key flaw in these schemes, at least in our models, is that they struggle to predict like really small values. They're getting the tails right, and then again, UNet is performing better. The M3 model is performing better than M1 and M2, but then it fails to predict really small values. I'll skip this figure, but it's essentially saying the same thing. Now, what I've shown so far is step 1, where we only train the model on error 5, but it does not resolve the whole gravity wave spectrum. So now step 2 comprises of transfer learning, where we retrain parts of the model on super high resolution 1.4 kilometer IFS data. And so now if we look at this figure, so this is the climatology, or this is the seasonal average from error 5 for 2015 northern winters. This is the profile we get from IFS. Before transfer learning, we see a nice agreement between the predicted fluxes from our models, but then if we try to predict the same fluxes for error 5, we get notable weaker fluxes, right? The fluxes here are much weaker than here, so the model is not really getting the magnitudes correct. But after transfer learning, we do notice that the model learns the IFS climatology well, so it's like correcting the magnitudes based on its previous training and getting a distribution which is closer to what we see in the high resolution model. And then if we simply compare, if we run it again after transfer learning on error 5, we notice that again the spatial distribution is quite similar to what it was before transfer learning, but then now there's this correction of fluxes thanks to the transfer learning on high resolution data. So essentially, this shows that there's a possibility, there's a potential to mix different data sets, different high resolution data sets, to train a machine learning scheme that can, that would be more generalizable and kind of provide correct flux magnitudes throughout the atmosphere. I mean, I don't have, yeah, that's pretty much it. Do I have time? Yeah, so I mean, we recently submitted this paper to James. It's under review. Please feel free to have a look at it. But essentially, I know I've sort of discussed a lot of information here, but essentially, the key takeaways are that machine learning trained on machine learning schemes trained on like higher resolution data tends to learn the physical properties of gravity waves and represent them, and possibly represent them better than the traditional parameterizations. Our transfer learning experiments indicate that different high resolution data sets, which are sort of sparse, not available for a long time interval, and so on. It's possible to combine different data sets to create a scheme that learns the best from all data sets. Now again, there's this limitation that I mentioned. We are working on it. Why the model fails to predict these really small values, which form the weak part of the gravity wave field. And then there's other tests we are working on right now. First is simply testing how our scheme performs on different model outputs from different sort of models with different underlying numerics, like the ICON model, for example, or high resolution vacuum runs. And then we are also trying to, we are also working on the most stringent test, which is what happens when we couple this scheme with the with the climate model, with CAM7 in this case. And does the model blow up? Does the model perform well? Do we get the QBO periods right? Do we get the stratospheric warming frequency right? Do we get the polar vortex erosion in the southern hemisphere, the timing of that correct? Yeah, that's a challenge we're facing right now, because coupling the M1 model is sort of straightforward, coupling it to CAM, but then coupling the M3 scheme, which requires collecting global data from all processors, is a challenge. But I've talked to some people here today during this workshop, and I've had some promising leads. So hopefully, we'll start working on it. Thank you.
Thank you for the presentation. When you went from M1 to M2 to M3, did you maintain the structure of your ML model, or did you change it? And if you changed it, are the improvements due to the non-locality or the difference in structure?
Yeah. So when we went from so between M1 and M2 have a very similar structure, with an exception that we have a convolution layer, a single layer in M2, which is not there in M1. And then we've tried to keep the hyperparameters as identical as possible. M3 is quite different from M1 and M2 because M3 is a convolutional neural net-based architecture. It uses something called as an attention unit. So it's completely different from M1 and M2. But then if you look at it, the training samples for M3 are much less than M1 and M2 as well. So the fact that it's performing, providing better results, even if the number of training samples are less, it's quite noteworthy.
My question is related. So for your M3, the UNet, it's more like treating a 3D field as 2D images with a segmentation, and the different images representing the different vertical layers. So I would guess it's very easy to reproduce this horizontal propagation, but have you ever looked at whether this machine learning model is reproducing like the vertical structure?
Yes, I don't think I have a plot here, but we looked at the variability and the vertical profiles. It matches pretty well. We discussed that in the paper. Sorry, I don't have it here.
Hi, Gupta. Very nice talk. So I have a question regarding, so do your machine learning model have any forcing input? Because like you are training the model using the era 5, say for example, present day. With the present day training, do your model have the capability to give the output for different kind of forcing, like historical or the future scenario forcing?
Yeah, I'm not fully sure. We don't have any forcing.
Because the system is not linear. I mean, it's non-linear
Yes.
thing. So your input have some sort of forcing thing so that it can do, like if the forcing scenario change, how it can change.
There is no climate change signal that we use in our training explicitly. The hope is, and I've not tested it yet, so I can't say for sure. The hope is that it learns the connection between the wind shear and the wind profile, and it learns the location where the waves dissipate. So I think that should, despite a changing wind structure in a changing climate, if it learns that, it should be able to provide plausible predictions, but yet to be tried. Thanks, great question.
Thank you.
Awesome. Whoa, he's allowed. I have a question for you. Great talk, by the way. So when you moved from M1 and M2 to M3, there's sort of a significant jump in complexity of the network. And thinking about your last point here, the technical aspects and also like the speed aspects of putting that back into a climate model are probably a significant jump. Have you done any testing on and off a GPU to see what kind of requirements this would put on the actual climate model when you're moving it forward?
Yeah, I haven't benchmarked the speeds yet, so I can't say for sure, but other people have sort of trained similar schemes on parameterization data, and they've found that they don't get a speed up, but they don't get a slowdown either. So it sort of remains the same. But then we are trying a new approach to couple the models to CAM, so we are hoping that it will be faster. But again, I can't say for sure. Maybe in a month I would have better answers. And in terms of M3 and M1 and M2, they don't have, they have very similar number of parameters. It's not radically different. So, and M3 is definitely faster to train than M1 and M2, maybe because of some optimized performance. I don't know, maybe it's a structure because the fields are like tensors rather than single columns. I don't know. But yeah, in that sense, they're not that different. So it's not like that the number of parameters are radically different that gives them an edge over the others. Yeah, thanks.
We'll move on to our next speaker. Our next speaker is Ram Saravanan.
So good morning. I'm going to talk about data-driven models for predicting precip. The first author is Tiju Chen, who's my grad student, who's not here, who's online. The photo is just an ad to publicize him. The other collaborators, Courtney Schumacher, Istvan Junyok, and Raymond Wong, all at Texas A&M University. So I'll talk about philosophy of machine learning first. I'm a physicist, I'm a climate modeler, and I think of machine learning using this quote from William Gibson, which says, the future is already here, it's just not evenly distributed. And you can use that for many things. You can talk about EV adoption, you could talk about impacts of climate change. can also talk about machine learning in the sense when you use machine learning to predict, you're assuming some part of the future is somewhere in the phase space. It could be in time and space, in the training data, and that's your motivation for predicting, using machine learning for predicting. And one way I think about it is that people say you can learn physical equations using ML or AI, and one of the fundamental equations is the Clausius-Clapeyron equation. It's going to tell you how intense precip is going to be. And if you look at the bottom, it's extremely complicated. And if you had data in that dotted box that you see there, and if you train a model on it, it might fit a quadratic or a cubic. It's not going to fit that really complicated looking expression. You need lab experiments and physics to do that. So machine learning has limitations, and but if physics-based model isn't working well or it's too expensive, I'm willing to consider machine learning. So those are the two cases I would consider machine learning, and I'll say those are the cases I'm encountering right now. So we know that machine learning models predict weather very well. I'm not going into the details of this plot. I'm sure you've seen it in many places. It's from WeatherBench. Typically, they predict geopotential, temperature, winds, things like that. Blue is good, red is bad, so there's a lot of blue out there. But precip is a different story. Machine learning models are doing precip, but sometimes they don't do it at all because it's hard. And sometimes they do it large scale. And if you want very regional precip, it's hard to do with machine learning. Okay, so machine learning is still not doing as well with precip as it's doing with geopotential, for example. And it's rapidly evolving, so someone might publish a paper tomorrow saying this is solved, but things happen very fast, but this is the current state. But precip is interesting. It happens on kilometer scale, and I was hoping to attend the other session to talk about kilometer scale modeling, but, and it's local. The local temperature, the local humidity, and some say local winds affect precip. Something happening 100 kilometers away isn't going to affect precip immediately here. It can affect it after some time. So there's physical concept of, there's no action at a distance in the physical mechanism of precip. So, and how we represent precip in a climate model with say 100 kilometer grid, we can't do the kilometer scale representation. So we do subgrid scale parameterization based on some physical assumptions. So the way it works is you run the model out to climate and look at the simulation of precip. And this shows climatology of precip and a persistent problem. I've been in this field over 30 years, and some of these problems go back a long time. And that one of them is the double ITCZ. And what you see here is the observations. There is no double ITCZ in this part of the Pacific, and models tend to do that. And this is a persistent problem, and physics-based approaches haven't solved that. Okay, so you might want to consider alternative approaches, and that's how I came up with machine learning. The other problem that physics-based models have is the high-frequency precip is not represented well. GCM drizzle rather than have intense rain, and in terms of climate change impacts, that's an issue as well. So physics-based approaches haven't done that well in simulating precip, and this is going back decades. So this shows, in this figure, what it shows is GCM's rain rates in the x-axis and frequency in the y-axis, and observations. The very high rain rates are not simulated by climate models traditionally. With ultra-high resolution, there's hope to improve it. Again, that's expensive. Okay? So if you don't have the resources, then what can you do? So the reason to do precip is that physics-based models still struggle with it. The other reason is there's lots of data. There's lots of satellite data. And the hope was that we can do pure data-driven models to predict precip. That was my initial question. This predates deep learning. Can we do precip prediction with just pure data and no physics? And why the 1D approach? I'm going to use a 1D approach, and that mimics GCMs. It has the physical properties. It has no action at distance. It has translation invariance. So what works in one region works in another region at different times. That's a fundamental physical property. And that makes it more generalizable for climate applications. So that's the hope here. So about 5 years ago, we did a basic statistical model using a technique called generalized linear modeling. And we built a statistical model to try predict precip using a column approach. And we did it for the tropical Pacific, where precip is very important to predict. We used logistic regression and gamma regression, and in the regions that are shown here. And then what we found was that The model, the simple column model, statistical model, can predict the spatial structure of precip fairly well. So in terms of climate applications, it did a pretty good job. And we did different types of precip in this. And we used track satellite data using GPM and TRIM, so actual active sensors rather than passive sensors. That'll become important a bit later. So we used the best precip data we had and tried to predict it. And we used mirror reanalysis for the flow conditions. And so the model did a decent job predicting the spatial structure, but it still struggled with the high frequencies. It was a sort of a linear model. It tended to be Gaussian with some transformation, log transformations. So this shows, again, the model precip, drizzle, observations, high frequency, intense rain. And the generalized linear model didn't do much better than the GCMs. So that was the basic statistical approach. And then more recently, we started using deep learning approaches. We use something called over-parameterized networks, where the number of parameters vastly exceeds the number of data points. And this shows the loss function. And it's interesting that statisticians don't overfit, but in machine learning, that's pretty common. And actually provides benefits. And we found that the over-parameterized model did pretty well. It did a lower error rate in predicting compared to other approaches like generalized linear models or random forest. The over-parameterized model did a better job in getting the error down in the two regions we considered for the three types of rainfall. It also got the high frequencies better than the generalized linear model. So we're making some progress with predicting precip using pure data and flow conditions derived from reanalysis. So this shows the, again, the rain rate, logarithmic percentile here. The observations is here, and the over-parameterized network is here, and the GCMs typically are here. So the over-parameterized network is getting the high frequency right, and also getting the mean more or less right. And then the idea was to see if we can actually go and put this in a GCM eventually. We're not anywhere close to that. But then we started building a model where we can use output of ML models for flow and try to predict rain. So that's the next step we're working on currently. So the plan is to use a 3D ML model, maybe GraphGAS or ForecastNest, get the flow conditions from there, and feed it to a 1D machine learning model, a column model of rain, and then try to predict. And we started doing it with ERA5 for input and the output, the flow conditions input, ERA5 rainfall output. And then we started thinking about doing a pure satellite product called iMerge. So we're working on it, and we're encountering some difficulties there, and that's what I'm going to talk about. So the data we're using is ERA5 quarter degree, and we have 4 years of training data and 4 years of test data. We're looking at summer rain in the Western Pacific. We have 13 levels. We use elevation, and we're looking at the Papua New Guinea region, so the elevation plays a role in affecting precip. And we also tried putting a lat, lon, and local hour as sensitivity studies to see if that affects the machine learning prediction. And initially, we did it with ERA5 to see if ERA5 data set can be predicted. And then later, we'll do it with the iMerge product, which combines GPM, TRIM, and IR to fill in gaps where the active sensors tracks are not available. We used multi-layer perceptron, very standard technique. This is some machine learning details. I'm not an expert on that. My student can answer some of the questions. But we had 3 million samples and 24 million parameters, so it's over-parameterized. And so the input is the flow conditions, TUV, relative humidity, output is precip. And initially, we're doing it just for ERA5. So the model, this model does a decent job getting the spatial patterns right. On the left is ERA5. On the right is the 1D model trained on ERA5. And it's getting the basic structures right just with a column approach. And we do RMSE and median absolute error. Again, the first column is using only TUV and relative humidity. And then we added lat lon to see if that makes a difference in prediction. We used the hour of the day to see if we can get the diurnal cycle better with that. And they didn't make a huge difference. The model was caring only about the flow conditions, not about these extra geographic or temporal parameters, which is a good thing, it's more physical. So we have translation invariance in the terminology of physics in this case. But if you look in detail, the model does well for synoptic conditions, large scale, thousands of kilometers, that's on the top, ERA5 and on the left, and machine learning on the right. For smaller scales, it's having difficulties. It's not doing as well. That's what you see at the bottom. Left is era 5, and right is model. So it's not doing that well with a smaller scale precip. The annual climatology, again, the model does a decent job, but there's some offsets, and it's probably related to how orography is represented. So the next step was try and predict I-merge precip, which is more direct measurement of rainfall, with era 5 flow conditions. And what you see in the top row is just comparing I-merge to satellite data set in era 5 for 2 different days, and you can see the differences. So I thought we had good data for rain, but in some sense you don't have good data for rain. And that becomes, I mean, if you remember Jonah Shaw's talk from the first day, we don't have true data. All data are contaminated by some kind of model in some sense. And then we did a pattern correlation between I-merge and era 5 using different accumulation intervals. That's what you see at the bottom. If you average 1 hour up to 5 days, and there's a pattern correlation in the Western Pacific, and you can see they start to agree as you go to longer time scale, but they don't agree in very short time scales. Okay, so we don't know what the truth is for rain. And so this is actually my conclusion slides, which are preliminary, so we're still in the middle of this. So you can have an E to E model using era 5 flow to predict era 5 precip. Does a good job. But if you use the same model but try to predict I-merge precip, it doesn't work because the 2 precip are different. We have been trying to train a model, take era 5 flow input to an I-merge precip. It actually doesn't work that well as the E to E model. Right? And that's where we are right now. And the way I'm trying to understand is that the small-scale flow features in era 5 that are consistent with its own precip, but not consistent with I-merge precip. And if you understand how reanalysis works, it ensures consistency. And so small-scale features in era 5 are also some kind of fiction. So we don't know the small-scale flow features. We don't know small-scale rain features because I-merge itself is a combination of passive and active sensors and involves retrieval, which involves assumptions. So in some sense, we may be able to predict only spatially and temporally smooth precip using machine learning because we don't really know the small-scale features in time and space. I mean, I-merge is 30 minutes time, 10-kilometer grid, but I don't think we really know things on that scale. Smooth prediction may be okay for weather, but if you don't have these, the physical relationships there, it's more a statistical relationship, then you worry about how we'll generalize to climate. So that's where we are. Thank you.
I'll ask a question. Thanks for your talk. How did you come to the choice of over-parameterization?
There's an earlier paper where we didn't do that. It didn't do that well, and we found that it works much better. Yeah, it's more trial and error.
And what are the compute requirements of training something with?
These are one reason we did the 1D was very cheap. We can do it. I mean, it's negligible compute requirements. Yes, it's a 1D model. This is basically unfunded research. We don't have big computer or time money allocations.
Very interesting talk. I was wondering, have you looked at using like those 20th century simulations, the output of UV and TQ, and your model to predict precipitation? Does it get rid of the double ITCZ problem that you mentioned at the beginning of the talk?
Could you say the 20th century analysis, you're saying?
Well, use the model data, the model UV.
Yeah,
TQ.
my goal was to do pure data, which you can realize I'm not sure we have pure data, but I didn't, when you use machine learning to emulate data, you get a model. When you use machine learning to emulate a model, you get a faster but slightly worse model. So I want better model. So
Right. I was just thinking, so you have this trained model that was trained to use observation and to predict the observation. But if you use the model simulated TQ UV as the input and the same model, the same relationship that you find from the observation, do you get rid of some of the model predict precipitation biases, which would suggest potentially those biases are, like you mentioned, due to some of the smaller scale processes, parameterizations, but not due to maybe simulated flow field or something.
sorry,
like that.
I'll talk to you later. I don't fully understand your question, but with ERA 5, we thought we were doing a consistent, because ERA 5 precip is controlled to some extent by the model. So it is consistent with the flow in era 5. So if we did this for a model flow and model precip, we probably do a decent job, I think.
Right. Okay, we can talk later.
Yeah.
Thanks.
We should move on, so thank you. Our next speaker is Sene Van Loon.
All right. Yeah, I'm Sene Van Loon. I know the Van Loon name carries some weight at NCAR. I am not related to Harry, and I've never even met him, but same last name. So I'm going to talk about some work we've been doing at Colorado State, just north of here, together with Maria Rugenstein and Libby Barnes. We have a related paper accepted in GRL. It should come out any day now. So recently there's been a lot of machine learning based climate emulators coming out that replace traditional climate models. And I say climate models, but it's at this point mostly atmospheric models that replace this with purely machine learning based things. The benefit of it is that it's fast and a lot of weather models have been coming out, but now also some of these models are stable on climatic timescales. So you can run them for 300 years without any problem. So one of them is the AI2 climate emulator ACE that has been trained on a couple different data sets. For example, FE3 GFS, the E3SM atmospheric model, and ERA5 data. And there's also the Camulator now that Will Chapman will talk about later. That's based on the credit architecture and trained on CAM data. But with actual climate models, we have since the 60s been trying to evaluate them and building trust slowly. And these climate emulators have been coming out over the last couple of years, so we need to be able to evaluate them to see if we can actually use them for scientific discovery. We propose one way of doing this using idealized batch experiments called Green's function simulations that are essentially SST-forced simulations with localized perturbations, and I will go into more detail. And we can call this some sort of distillation model of the emulator. So I will mostly be talking about ACE, the AI2 climate emulator, because the ratio was offline, as you know, last week, so I couldn't do these simulations in Camulator, unfortunately. So ACE is an autoregressive model that's it's atmosphere only. I show here some of the inputs, and so forcing is SSTs, CI's fraction, incoming solar radiation, and CO2 concentration. So it's a typical atmospheric model that you can run AMIP simulations with. And it predicts, based on the current state of the atmosphere, it predicts 6 hours in advance. And that's what it's been trained on, just this 6-hour time step. And still, it's kind of impressive that just by learning the 6-hour time step, it's stable on century timescales and can predict a reasonable climate. So these are the 3 versions I've been testing. I've mostly been interested in the ERA5 version, so that's trained on reanalysis, but it's also trained on the E3SM atmospheric model and GFS. So the nice thing about these emulators is that they're very fast. You can get about 1,500 simulated years per day on a single GPU, as compared to way more with traditional models. So we can run these simulations very fast. So Green's function simulations, a Green's function in general is a way to solve a linear differential equation. So in our case, the differential equation is solved generally by a GCM. We do have to, this Green's function is a linear method, so how you find this G, the Green's function, is by forcing the model with localized delta functions pretty much. So in general, you get a forcing and a response, F and R, to a linear operator. But if you do this with these delta functions, you get the Green's function, and that represents a general solution of this linear differential equation. So what we do in atmospheric models to get to this Green's function is we run a lot of simulations. We start with just an annually repeating SST climatology. So this protocol has been described in this GFMIB, Block-Johnson. This should be 2024, actually. But these simulations have been done in atmospheric models for a while now. So you start with this annually repeating climatological SST, and that's the baseline control simulation. And then you run these separate batch simulations. So on top of the annually repeating SST, you take one of these batches and increase the sea surface temperature in that location. It's usually a cosine batch, so it's kind of smooth. You run the simulation for about 10 years and calculate some value that you're interested in. I call this F here. So, and you subtract that from the control to get your average response to this localized batch perturbation over 10 years. And then you move on to the next batch and so on. And so there's about 100 batches here that you have to run for 10 years. So in an atmospheric model, this is quite expensive. It takes a couple weeks to do these simulations, but people have done it. But in these emulators, we can do it in a couple days. What you get then is you can calculate the so-called Green's function, or this is the response of a certain variable that you're interested in with respect to sea surface temperature. And so you can think of this as trying to calculate the numerical derivative of this variable that you're interested in with respect to SSTs. And so this Green's function really represents a linearized response to of the climate to SST forcing. So a little bit as a sideline, these Green's function simulations in the last couple of years have mostly been used to study the radiation budget of the Earth, and that's why we wanted to try this in these emulators too. In the global mean at the top of the atmosphere, the radiative imbalance, N, is equal to the rate of forcing plus the rate of response. The forcing is the excess energy we put into the system, and the rate of response is how the planet responds to that. And so only N, the rate of imbalance, is something we can measure, and to get the forcing and the response, we have to rely on climate models to get that. The rate of response is usually written as linearly rated to global mean temperature with lambda here, the feedback. But this feedback parameter tends to change depending on how the SST warming occurs. So to move from this global mean feedback that changes over time to a localized feedback, we use these Green's functions. So this is an average Green's function map calculated in different atmospheric models. And so this is one of these Green's functions, and it shows that the local feedbacks. And so if you would multiply this with an SST map, you would get your rate of response. So instead of having this global mean lambda times T, we actually have a map of local feedbacks times the full map of SSTs to get the rate of response. And so this is what you get in atmospheric models. The hatching here is where the models do not agree on the sign, but in general, we expect these feedbacks to be negative in the West Pacific, where there's convection, and then positive in regions of stratocumulus decks, because if you, in these stratocumulus decks, if you heat the surface, you evaporate away the clouds, so you get a positive feedback, while in the West Pacific, for example, you tend to heat the top of the clouds in the East Pacific that actually stabilize those stratocumulus clouds and stabilize the atmosphere. So what does this map look like if we do this in climate emulators? This is what we get in ACE Era 5. And it looks surprisingly well. So it's trained on only Era 5 data. So it's closer to observations than we can get with models. And it gets the same features of negative feedbacks in the West Pacific, positive feedbacks in the East Pacific. And again, this was trained on 6-hourly data, and on climatic timescales, we get a reasonable looking Green's function map. If we do this in the EAM version, it also looks great, I would say. If we do this in ACE FE3, it does not look what we expect it to be. And in particular, you can really see the patch structure in this. Like you can see where the patches, the SST patches were forced, which means that there's some kind of weird response going on in this model. We hypothesized that it might be due to these models not being, because this is a numerical weather prediction model, they don't have energy conservation. So this might be the reason that they don't get it. We can use these Green's functions to reconstruct the time series of the radiation. So again, this is this global mean framework, and by multiplying it with the SST maps of the historical that we observed, we can get the time series for R. This is what we get from the ACE Era 5 Green's function map, and I'll put these up here. The gray lines here is the predictions from that we get from GCMs, and that's what we expect. We expect this time series to go down because we force the system, so the response has to be we want to send out more energy. And so even though this ACE Era 5 and ACE EAM Green's function maps looked reasonable, if we use them to reconstruct the time series, it really doesn't work. The ACE Era 5 one actually has a positive trend, which is definitely not what we expect. The ACE FE3 one actually does better in the internal variability, but it has some weird decadal variations that shouldn't be there. So the question is, can we use these climate emulators for scientific discovery? I think we're not there yet. But if we could, they do offer some nice benefits. For one, we can probe the observed climate system in a new way. Because these Green's functions, in principle, they turn off the forcing. So it's been trained on historical climates where we cannot turn off the forcing, but these Green's functions offer a way of doing that. And although I focused on global mean radiation, I want to emphasize that you can use any variable that you want. And this is just as an example. You can study the effect of warming in the West Pacific on the 500 hectopascal geopotential height, for example. This is in ACE Era 5, and it looks kind of what we expect to. So even though we find a physically realistic sensitivity map in ACE, it fails to capture the expected negative trend in the radiation. And so we think this might be due to lack of energy constraints. And this is one reason we want to try this in the camulator, because it actually has physical constraints built into it, and you can turn it off and on again. So we want to do these Green's function experiments in camulator using with the physical constraint and without, to test this hypothesis. And in a sense, this looking at radiation is just because they've been used for radiation for a while now, but we do not know what this true sensitivity looks like. So even though we have some idea from the models, we do not know if this is the truth. So Using Camulator, for example, we can actually compare directly with simulations in CAM. So finally, back to this idea of distillation model. These emulators really need systematic testing, and that can be done by doing forced simulation runs. There's multiple ways of doing it that people have been using for traditional physical models for a while. We argue that Green's functions should be part of this systematic testing, and so because they can distill this nonlinear statistical black box of the emulator. So just as if you would make your favorite whiskey, you take a distillation machine, you input the emulator, and out comes the Green's function. And so this is what you miss is all the nonlinearity, small scale features, short time scales, but what you gain is this physical understanding of these Green's functions. We have an idea how these Green's function maps should look like. We have an idea of how the climate should respond to a localized warming, for example. So for one, this is an out of distribution test because these localized forcings have never been seen during training. It's a linearized causal response, and they're physically interpretable. So I'll leave it at that. Thank you.
Thanks, that was really neat. I was wondering, so you said the training had never seen these responses. I feel like there's several examples where these emulators aren't getting good information about the Jacobian from training on time stepping. Do you feel like the way forward is to keep training on the time stepping, or do you need to include information about sensitivities explicitly in training?
That's a good question. It could help or it could not help. I think that's one of the things we need to understand, like how does it get the climatic timescales correct by training on 6-hourly time steps? I do not know. So it's one possibility to try to get that in there, but I wouldn't know how to, actually.
We are checking Slido, so if you have any questions online, please put them there.
A nice talk. This is more a comment than a question. I just wanted to highlight that the models we're training on, like the reanalysis system or the Earth system models, like they don't conserve energy for the right reasons. Like we use energy fixers, and regionally they don't really close the energy budgets very well. So it sounds to me we have some work to do in the traditional modeling space as well to train these emulators.
Yeah, that's fair. It is. It was just said that these emulators are always going to be worse than the training data we put in. And even if we have a perfect model, yeah, we need the correct training data, but we don't have it yet.
Great, thank you. We'll move on to our next speaker, Dave.
Okay, thanks. That was great. A lot of perfect talks to lead into this. So I'm going to try to motivate the group to be thinking about how we're to move towards a machine learning enhanced version of CSM, sort of taking advantage of a lot of these new machine learning capabilities that we're learning about to make a quantum step in the quality of CSM to build, essentially to answer that question, to build a better model for training for emulators. Probably won't get to the emulator part in this talk, but it's part of the overall vision here in the CSM activity. So I start with this slide in most of my talks these days, which is a figure from Veronica Eyring's perspective paper that I was a co-author on along with Pierre Gentine and others, which sort of outlines a vision for the sort of the future of Earth system modeling, next generation Earth system modeling. So if we go into the perspective that one of the there's lots of reasons we build Earth system models, right? But one of the fundamental reasons in the climate science world is we need to provide actionable, reliable, relevant, and accurate information for stakeholders, users of the data that are trying to make decisions related to climate change. If you say that's a core reason we're doing this, then we need these models to be getting better. So models have been getting better over time. CMIP 3, 4, 5, it wasn't a 4, we skipped it, 5, 6. The models have gotten better, but it's slow, like a painstakingly slow process to make these models better. The physics is getting better, but the quality of simulations is getting better at a relatively slow pace, although at least it's steadily getting better. And so the big question is, can we accelerate that using machine learning? Because the urgent need for this information. At the same time, there's kilometer scale models that are being developed. There's other high resolution models like LES or genetic numerical, which we know are providing, in a lot of cases, more accurate simulations for at least specific parts of the system. Less reliance on parameterizations. And at the same time, there's an increasing array of Earth observations. We know we're underutilizing them in the development of our models and also in the evaluation of our models. And then also at the same time, we know that large ensembles are going to be required for us to understand the role of internal variability for trying to understand the uncertainty in climate change projections. So you cannot most likely rely on these kilometer scale models, even if they got to the same quality that we have now or had all the features, because it'll be almost impossible to run ensembles. Maybe with an emulator you might be able to get there. That's another question. But so in this world, then the framework we're putting forth is that we need to try to, well, we don't need to, but one option is to try to build hybrid models, which is combining machine learning based parameterizations, machine learning based calibration technologies to really make a step function change in the quality of our Earth system models. And so it's sort of the way all these kind of pieces of the model development world are working together: kilometer scale modeling, LES, Earth observations, and machine learning all coming together. And then you can then take that information and use machine learning again to do downscaling, regional refinement, et cetera, to drive impact models. So that's a framework. Fortunately, within CSM, we have these two pretty big activities: the Learning the Earth with Artificial Intelligence and Physics, which is the LEAP project. It's NSF Science and Technology Center. It's about a $25 million project. Hopefully, will be renewed for another 5 years. And then also the M-Squared Lines project, which is supported by Schmidt Sciences. And both these two activities are working to do exactly this, which is to bring new machine learning-based parameterizations or parameter estimation or optimization technologies into CSM to build the next generation CSM that will hopefully give us more accurate projections. And so I'm going to start off with a few things that we've been doing. One is working on machine learning enabled parameter optimization. This is mostly coming out of the LEAP activity. And most of those of you who were here this, for Monday saw me give this slide. And basically we made a lot of progress within LEAP towards this. So on the land side, in both the land and the atmosphere, we've started there. On the land side, Linnea and Katie and Daniel Kennedy have been building up a set of tools that allows us to do parameter optimization and uncertainty quantification within the CLM. And that's drawing on some of the capabilities we've built up over the last few years to be able to really have a really fast version of CLM, which allows us to run large ensembles. And then we're using a history matching approach to kind of iteratively walk through and throw out parameter sets which are not matching up with our observations or not consistent with observations, and we can kind of iterate and focus in on the particular regions. I will say here we're getting strong evidence. I've seen this every time I've seen somebody try to take on the parameter estimation. Problem is it really requires not just all the smart math and machine learning based capabilities, but it needs the domain expertise of someone like Linnea or even the whole land model working group to really understand how to approach this. It's not just you throw math at the problem or you're going to solve it. It really needs to have this really in concert the development of these technologies. So this work is going well. We're actually using it to calibrate CLM6 right now, of which we're going to CSM3, so the one machine learning based piece that's going to be in the CSM3 hopefully. And then on the CAM side, the work is kind of building off of work that was done originally with the GIST model to use 30 or 35 different, mostly reanalysis type data sets as calibration targets, and they have a set of methodologies to work on that. And then we've been adding to that in ways that I probably can't characterize very well here, but using this thing called the additive Gaussian process emulator, which is having nice features and trying to build that into the CAM structure. And again, we are using this not the full-blown set of tools yet, but we are using some of the capabilities in the sort of tuning and calibration of CAM. And I like to I think Linnea actually coined this first, so machine learning assisted hand tuning. So we're still back in the Stone Ages, but we are at least using machine learning a little bit to assist us. So these are two nice activities that we're building these capabilities in. And one I'd like to show this slide is sort of saying one of the features that they're coming up with is they learned with the GIS work and it's showing up in CAM2 is that, you know, when you first do a parameter sensitivity assessment of your model, you might find that there's some insensitive parameters that don't look like they're important, but actually they can either be cumulatively important as you kind of look at when you add them together, or as you kind of zero in on the actual correct parameter space, you find that a whole bunch of parameters that weren't originally important become important. And we're also finding that some parameters are only locally or regionally sensitive, which is interesting, and that allows us to be starting to think about how you can target specific regions if you have a problem in CAM or a problem in the climate simulation with a bias. You actually have the possibility of, you know, if you have a problem in Indonesia, we have a parameter here which can just target Indonesia, which would be kind of nice. So this is nice work. On the CLM side, I just want to emphasize this thing about we're using this for uncertainty quantification as well, and so you can sort of progressively bring in new constraints, observational constraints, to constrain, in this case, the land carbon trajectory, which is a really important uncertainty in the climate system. And so we can find out, you know, go from this really unconstrained situation to a relatively constrained, and then we can then consider doing a few things. One is publish an observationally constrained perturbed parameter ensemble. So when we publish CLM6, we're going to publish 100 parameter sets for the community to use if they want to try to explore uncertainty. I think that'll be a kind of a new and unique and innovative thing that we're doing. And also we could consider a future CSM3 large ensemble that is, you know, spanning across this uncertainty with, you know, all these things being reasonable parameter sets, and we can, you know, especially in emissions-driven mode, you could see really different behavior as you go from one of these that's, you know, has a low carbon sensitivity to a high carbon sensitivity. So kind of excited to think about that. We could also span, using the CAM ensemble, different ECS or TCR values. Okay, moving on to ML-based parameterizations. There's a lot of activity here, and so one of the activities that we started with is this machine learning warm-rain microphysics, an activity that was led by Andrew Gedman a few years ago, and now we're bringing it fully into CAM. And what we're seeing is that when you bring it fully into CAM, we can replicate some of the improved tail behavior that we're seeing in extreme precipitation, which is nice to see when you sort of replace this so-called tau microphysics, highly resolved tau bin microphysics scheme with a machine learning based one and put it into CAM, you can get good behavior. So that's showing that, you know, we can do this. Now in this case, we hard-coded this neural network into the model, and I'll get to this in a moment about why obviously that's not the way you want to go in the long run. That was work that DJ helped out. Well, I'm going to see him here in the front row. So and Adisu, who's in the audience somewhere as well. So, but one thing I want to point out here is that, you know, it's good to have these capabilities, and what we're hoping to see is a big step change in things. And so the model is going to hopefully, in some sense, look really different than it used to. And we know that, you know, in the past we've had to like then calibrate it back, get all the things that we've, you know, calibrated, spent years, decades even getting the model to look right. If you make a huge perturbation to it, then it's going to take all your time is going to be spent like getting the model back into some sort of a shape that you can use for. So I think it's really important to have this. You know, this is an example. This is just an example. It's not an actual result, but just say, you know, maybe we've tuned our shortwave cloud radiative forcing really accurately in CAM. Then you throw in this new thing, and it all looks totally wrong. You know, cloud radiative forcing is again, and then you have to have the two experts in the world who know how to tune that back, and then you're stuck, right? And so the idea of having this machine learning auto-tuning is like a really critical piece here. They need to go in concert. If you don't have this, I think you're going to be spending all your time recalibrating your model. So we're really trying to bring this, accelerate and push on this part of the problem as much as possible at the beginning, so that we're ready when all these new machine learning based parameterizations come in. Okay, in terms of those machine learning based parameterizations, this is another figure from Veronica's paper, just sort of highlighting some of the possible ways. And everyone here in the room can come up with ways that you can potentially think about using machine learning to enhance a parameterization, replace a parameterization, either from a high fidelity model or Earth observations. It kind of spans all different aspects of the Earth system. It only, as you know, this is only restricted by our creativity, in my opinion. There will be situations where it's not going to be useful, but a lot of situations where it could be useful. And so within the M-squared lines especially, and the LEAP projects, we've now have a set of parameterizations that are being worked on. And these are what I'm calling candidate parameterizations and tools for the CSM3 MLE. So what you can see is we have 10 to 15 different activities going on across the CSM community or outside the CSM community, which we think are possibly candidates for being included into this CSM3 MLE configuration. And so I'm not going to go through all of them, but just show that it's spanning, the full gamut of their system. We're sort of doing that intentionally, right? We don't want to necessarily just focus in on one aspect of the system. And at the same time, we've also built in these capabilities to use FTorch to couple between the machine learning based technologies that you have in a PyTorch package into the Fortran code. And so again, we're trying to make it easier for any of you out there who wants to bring a machine learning based parameterization in. You can do that relatively straightforwardly. And last, I want to mention that this cloud cover one is actually coming from the ICON group, and they're going to be working with us this summer to see if we can translate an activity that was going on in a whole different model and bring it over into CSM. Okay, so one thing that's happening though, so as we looked at these 15 or so different projects, is that a lot of them were not making it, not making their way into CSM. And so why was that? Well, it's because we didn't have these interactions with the CSM core development team that we needed. And so what we've done then is created this new layer of people, which is, go from the LEAP and the M-squared line scientists, largely grad students and postdocs who are working on these activities, and then coupling into the CSM developers with this integration team. And Linnea and Will are on the integration team, and they're the ones who are really trying to, make this really happen. And then we also have project management to sort of track what's going on. And one of the first things that this team is doing is going out there and asking each one of those groups in a lot of detail, like, a lot of these groups are saying, yeah, my parameterization's ready to go. And then you go, okay, is it ready to go? And say, what does that mean? And you actually say, okay, we have a little bit of conversation with them and realize that maybe they're not actually training on something that CSM is producing. So they've trained on something external, and and they say we're ready to go, but actually CSM isn't producing that variable, so it's not actually consistent. So this team is going through and asking these detailed questions. We have survey responses for all these different 15 activities that really trying to get at the nuts and bolts, like where are you really in this process of being able to ready to go. So then, then we can start thinking about towards this machine learning enhanced CSM3 MLE, and I'm really careful about defining success. I'm an optimist, and I'm also a realist. Like, this is going to be harder than we say. It's really easy for me to get up here and say we're going to produce this. The reality is going to be harder than that, and the ICON group, who's a little bit ahead of us, is experiencing some of the challenges that we're going to run into. But we can define success however we want, right? And so we can define success as if we get a few ML-based parameterizations into CSM, and we can call that CSM3 MLE, and that'll be our first version. It's just our first version. We keep building on that. So it might be 1 to 2 in the atmosphere, 1 to 2 in the ocean, 1 to 2 in land. It could even be 1 in each one of those. I'd still call that a success. We have the capability to machine learning based parameter calibration, so that'll be a feature, so that'll be cool to have. We won't have tackled the coupled calibration problem, which is intensely difficult, I think. And we're excited to think about that. And if anybody has good ideas about that, we want to know about it. That's going to be hard. We know that, but we will at least be able to do this calibration offline. And then hopefully we're going to have reduced biases, significantly reduced biases in critical fields, especially extremes. So here's the final slide. Push forward to the next 18 to 24 months to test this hypothesis that ML can build better and more accurate ESMs. And we're going to hear a lot about emulators. I think emulators are awesome. We're going to use emulators to do a lot of things like filling out ensembles, really fast simulations. But if you don't have a high quality and improving underlying core Earth system model, all that work isn't really going to be able to really make the most benefit. So we need these sustained team interactions, more coordination, and then anticipate there's going to be challenges. Machine learning parameterizations in and out of training climates is an obvious one. That's something that everyone is thinking about. It's probably going to be new instabilities when you add these in, unanticipated interdependencies, substantially new simulated climate that may degrade orthogonal aspects of the simulation. Almost for sure that's going to happen. And there may also be new tuning challenges as some of our traditional tuning knobs are removed when we've gone to this machine learning based parameterizations. That's just another thing we may have to overcome. So I will stop there. And take any questions. Thanks.
Any questions?
Extremely exciting progress there, Dave. I'll come back to the point, or an alternative approach that might be worth considering at some point, which is you've got a system which has got well-known fluid dynamical equations, the Euler equations, and then a gigantic sea of mystery meat on the right-hand side of those equations with a very long list of processes that have to be tackled one after the other after the other. And I do think it is worth considering hybrid models of a second kind, which is where we emulate the left-hand side, the fluid dynamics, and use traditional physics. It is worth perhaps exploring both, and we're very open to doing that in concert with other people. The advantage of doing so, there are two advantages. First is you skip going through this laundry list of mystery meat of physics parameterizations. And the second is that because high resolution is totally dominated by the dynamical core in terms of the computational performance of the model, this allows you to very quickly get to ultra high resolution with emulation of the fluid dynamics. And the fluid dynamics is something we can tell if you're getting the right answer for the right reason. Much of the stuff on the right-hand side, God only knows. So just that's more of a comment than a question, but I'm really excited to see CESM pursuing this direction. It will be one of only 2 models in CMIP7 that has taken this step. So I think it's a very bold step for CESM.
Yeah, thank you for that comment, and of course you gave this comment at the advisory panel, so we heard you. I have not yet adapted my slides to reflect that comment because we don't have any real activities on that, but I totally agree with you that that is an opportunity that we should try to pursue. I don't think we necessarily want to drop the machine learning based parameterizations as well, because that could still be added on top of that if you really can improve on the physics which is underrepresented or understood. You know, on land, for example, we just don't know equations for photosynthesis or whatever, that fundamental equations. But yeah, absolutely. And LEAP is dabbling in this. The LEAP phase 2 is dabbling in this, exactly what you said. Probably not enough to bring it all the way to fruition, but yeah. But thank you, appreciate that.
Last questions before we move to discussion? Okay, great. Thanks, Dave. So now we have about 20 minutes for a general discussion. We have a question that we have for all of you. And I think what was clear in yesterday evening's session is that the community in CESM is what's really important. And as we move forward with our AI roadmap, we want to continue to engage. Your question that we have for all of you is what can NCAR do for you in terms of using machine learning in your own research or with CESM going forward? Nothing? Absolutely nothing?
A lot with machine learning. I'm wondering from a diagnostic point of view, we're trying to understand how our systems work, how the Earth system model works, how it responds to forcings. How can we build tools that are available to the community that really capture the best machine learning processes that are available out there? Like, so the barrier to getting into machine learning and understanding how to use the tool sets is quite large. So from a community perspective, how can we include these tools in the diagnostic tools that we're building right now?
Yeah, thanks for that point, Peter. I think, you know, one thing that's been done a lot is thinking about how to share basic tutorial materials for getting started with machine learning, but I like your point about the barriers to entry, and maybe we can also think about providing tools for folks who don't necessarily want to build the machine learning parameterizations themselves, but use tools to evaluate their science and do that as part of a standard diagnostics framework like Cupid. So it's a great question. We should think more about it. And we should really think about the usefulness of tutorials. Sometimes there's an overwhelming amount of material out there and it's hard to really know where to start. So pointing people to the right places for what they actually need is a challenge.
And it's a bit in response to Dave's talk. Thank you so much.
only want to partially re-invoke this discussion about parameter error as opposed to structural model error, because we know parameter, which, for example, mass flux, right, which can be a parameter. Obviously, if you perturb it, you're going to change the whole vertical structure of the atmosphere. So in a way, parameter uncertainty can be structural uncertainty. But I think it's a pity that we, again, focus on parameter estimation as opposed to structural model error. And there's a few efforts, really, that are focusing on structural model error, both in the atmosphere and the ocean. And I really would like to see them more included, because I think this is where the frontier lies of really coming out of this regime where we have convection parameterizing models that really miss out a lot of the high resolution aspects that might interact with things like sensitivity to response to an external forcing. So let's focus more on structural model errors. Thanks.
Very big barriers to entry in this field is the some of the computational demands, right? So training, not cheap. That's typically thousands, tens of thousands of hours on a GPU, not accessible, to many groups, especially, well, to many groups in general. One thing, but the emulation is fast, and if you can get that off of a supercomputer, then you're good to go. I do want to point out that this machine I'm holding in my hand has 30 GPU cores on it, right? So one thing that would be interesting to try is to port emulators onto laptops, and CUDA has been ported onto the M3 on the Apple M chipset. So, why not, right? This would be game-changing if people could run emulators on their laptops, and there's no reason why we shouldn't be. So, just a thought. One more thing for the software engineering working group to do. I'm sure they're welcoming that as a thing, as a to-do, but just a thought.
DJ, do you want to comment on credit and our ability to put it on a laptop or not?
Yeah, I can. So a couple of these points. One, I was able. So you have a relatively new laptop. I got one of our credit models to run on my 2019 era 8 gigabyte GPU laptop. So it's certainly possible. I haven't tried Camulator on my laptop yet, but I need to work with Will on that. I mean, it should theoretically work fine, because this was like a quarter degree 1 hour time step model that I ran on there. I think in terms of other barriers to entry, I mean, I think one thing I see kind of maybe coming from not of the climate community necessarily, but coming from the weather/machine learning community, is there's definitely I mean, some of it's a language and understanding, like, what are the, like, different variables and important things, how they relate to each other, and kind of also the history of all the different experiments and ways things are run. So I think in addition to, teaching climate scientists about machine learning, there's also a lot of room to be teaching machine learning and other people about climate science and kind of some of the history and, like, why are things done a certain way, or why do we include, why are these fields important? Because one of the problems we run into is it's easy to fit a ML model to data and not really and get a halfway decent result. But if you're missing certain variables or like not running it a certain way, that's where you get into some of these weird failure modes that show up. And so I think that's where we need to improve our dialogue. I think some of the efforts LEAP has done with, like, their ClimSim data set is a good step in the right direction, but I'd like to see more from the community. And it may also help us, like, reevaluate some of our assumptions and maybe see new opportunities in the process. So it's not just we're doing it for one way or the other, but I think there's joint collaborations that could come out of it that could be very useful.
Yes, I was a little confused by your comment, because I think that's exactly what we're doing, is addressing structural error while also having the capability to recalibrate the model after you've addressed the structural error. So, like we have several projects on replacing convection schemes, learning from high resolution, ultra high resolution simulations or LES simulations within leap RAM squared line. So I guess maybe we just need to have a conversation, but I feel like that's exactly what we're doing, is trying to tackle the structural error, and all I'm trying to do is prevent us from then spending all of our time trying to get the model back into a reasonable place. A model that's structurally correct, but like totally wrong in its climate simulation isn't going to be totally useful. So, but yeah, hopefully that I want to make sure that point is across. If we're not addressing structural error properly using these methodologies, then we need to be reconsidering what we're doing, I think.
I just want to comment on a slightly different topic. It goes back to Bill Collins' question about the right-hand side and left-hand side. I'm working on an ultra-high resolution project. The thing I worry about is that we do 1 kilometer runs, but the answers depend on microphysics. Depending on the microphysics, you get different answers. So you could train ML on an ultra-high resolution model, but if you get different answers with different microphysics, then you have different, the structural uncertainty is gone from the kilometer scale to the microphysics scale. So I don't know if the microphysics couples, I mean, it's difficult to completely decouple fluid mechanics. I think that we're not there yet, but I'm worried that's a possibility.
Hi, yeah, for that question, how NCAR can help us, like as grad student, I would say, like a lot of times happen, like I really like to know how can I use machine learning in my, like answering my research question. So I was thinking, yeah, tutorials or like kind of having like, if I can have like a big picture of which research questions like machine learning can answer. First, I think that would be good, like a lot of online like resources, tutorials, and also the second one would be like, how can I do it? But yeah, first I would like, first and most important, I like to learn is like, it's like machine learning is like unfamiliar for earth system science. And I think if there would be any way to facilitate that, like to like more like accessible for us and like answering more research questions, that would be cool if we know what applications we can use that and why we should use this, or as like kind of more like a statistical method that we know, being a little bit more familiar with machine learning, that would be cool. Yep.
Yeah, thanks, Ali. I really like that point about guidance on what research questions can be addressed with machine learning, because it kind of flips the narrative a little bit in the traditional sense where maybe we have these tutorials where we're overviewing a wide variety of machine learning methods, but in this way, maybe it starts from the reverse, which is to say, here are some research questions that can be addressed with machine learning instead of just putting a whole set of machine learning strategies out there. So thanks for bringing that up.
And then sorry to interrupt, Monica has a comment online that's related to this as well, about helping to train users about what responsible and reliable AI looks like in the climate modeling system, especially with respect to workflows. And then how do we determine the appropriate use of the data and models, and how can we add that into our training the community with these tools? So just building on that, how can we provide some guidance on using these tools reliably?
I was just thinking, while everybody's mentioned those perturbed parameter ensemble simulations are really expensive to run, and the value of it is obviously you can integrate observations to help improve parameterizations. But as we collect more and more observations, I feel like a barrier entry for general users could be, how do we find those simulations, those perturbed parameter ensemble simulations? They mentioned CLM is going to publish this 160 parameter ensemble simulations. That's great, but it sounded like there are a lot more of those simulations out there. So, like better documentation, not just like the simulation set, but also like the parameters. What do they mean? It's really, really hard to find those informations, and sometimes it's just like very short description. And when you read it, what do you mean? And the other thing is, as we seeing from paleoclimate perspective, some of those cloud parameters, when they perturb to simulate past climate, then that can actually provide a lot of additional insights in the couple system, although Dave said they're not looking at it. But sometimes those simulations really hard to set up. You have to ask specific people and what to perturb and how to set them up. So the other thing is for this new CESM3 Emily, is it possible to like develop some kind of configurations that people can run like perturb parameter ensembles out of box? So that would be useful. So that would be my suggestion.
And maybe also, because you're asking like, what can you do? I think we're all talking about tools and how you can help with tools, but one of the most important things from machine learning is the learning part. So we need good data sets that we can train on. I think often we forget like training data, what we put in, we are gonna get out. So if we don't have what we put in, we cannot get it like out of the machine learning. And if we put in garbage, we're gonna get out garbage. So it would be good to know what is out there, what is good to train on, what are the downfalls on training on one data set versus another data set. I think that would be very helpful, for at least for me.
I just want to respond to Ran's question or comment. Absolutely, I think that's the point. And what our goal is for, we'll get some of the way there for CSM3 is to release, the ensembles as well as all the scripting, all the tools to run your own ensemble, as well as hopefully some parameter estimation tools as well, so that you can try to do this yourselves. And we're really trying to, again, reduce the barrier to entry for this, and also to reduce everyone repeating all the steps. So we've done a lot of the hard work of identifying all the parameters, parameter ranges. We have a giant table, which nobody would want to look at, terrifying table. With all the information we're tracking, as we learn stuff about parameters, we're tracking that, so it's in that table. All that stuff we're going to release to the community. On the CAM side, it probably won't be quite as far along by the time of the release, but the same goals will be on the CAM side to have that capability. So 100%. My feeling is, with everything, parameter estimation is a science, and there's no like answer about how you do it, right? You need to build a flexible system that allows users to explore and learn on their own and test out their own new methods. So that is the goal for 100%. I feel like that's one of our responsibilities is to do that. So it's coming, hopefully.
Hi, thanks a lot for this forum. I got lost on the question we are trying to answer, but I think what came to mind, I don't know how much of this is an NCAR or a CESM thing that we can do, but I think someone beat me to it about data. I think we can try and advocate for more quality observation data over especially data sparse regions, because I mean the weather is connected and we don't expect things to work in isolation. So if we have quality data over corners and then we have bad data over Saharan Africa, what do we expect the weather model to do? Because we are using this data to train our model. So it'll be good to advocate for some quality observation data. And I don't know how much CESM can do on this, and I don't know how much NCAR can do on this, but I think it's good to put that out there. The second thing is to have more target-focused workshops. I know this is actually a good thing, like we haven't one here at NCAR, but it will be probably nice to have other hotspots, maybe in South Africa, in South America, in Australia, in Europe, where people can actually have hands-on experience and practice on some of these things we are talking about. Because I don't think NCAR as a building or even as a body can host all the scientists who are interested in working with CESM. So having more hands-on tutorials and workshops would be very helpful. Yeah. I hope I answered the question. And
Okay, great. It is 10 o'clock, so it is break time. I just want to mention that we will be talking about Camulator and credit after it. So if you're not familiar with those, which have been mentioned a lot, that'll be after the break. So. Okay, everyone, we're going to get started. Our first speaker after the break is Xavier. He is remote, and I'll just let you go ahead, Xavier.
Hi, thank you, and I'm very pleased to be here and to be able to present our work, which is the implementation of a neural network scheme to represent deep convection in CAM6. And I would like to acknowledge the funding, which is M Square Lines, as well as my team of wonderful collaborators, which are all listed on that slide, and many of them are actually here today with you. Okay, so I think that all of you are familiar with the fact that convection is one of the most is one of the hardest problem in atmospheric science, and also it is associated with many of the well-known biases that you find in atmospheric circulation models. The convection relies on representing a large array of physical processes. Some of them are poorly known or represented, and others are challenging to represent because of the scale at which they occur. The recent advances in computing power and algorithm makes it possible now to improve convection using a machine learning approach. And this is what I'm going to present today. This is ongoing work, and not all of it is perfect, but I think it shows promising results. So there are basically broadly two approaches you could take to look at this problem. One would be to use a existing convection scheme and improve the parameters values to be used. The other approach is to create a new scheme where you basically use like a neural network, and there is no per se underlying physics in the model, but there are constraints, and both approaches have their advantage and limitations. It is complicated to implement a new convection scheme since there are other schemes in climate models that may overlap and also you may have to retune the model potentially if you do so. So what we want to achieve today is to first produce a data-driven scheme that captures key processes in deep convection, try to port it to CAM6 CSM with minimal tuning or alteration, and shows that it can reduce biases in climatology and climate variability. So I won't do all of that today, but I will show you some of the steps that we've taken to fulfill these three goals. The first goal is to produce a convection scheme. So to do so, we've used a set of high-resolution SAM simulations, which have an effective resolution of 4 kilometers. And we coarse-grain those simulations onto a 96 kilometer grid. Using this coarse grid, we computed the grid scale and subgrid scale fluxes and tendencies, and we then use a 5-layer neural network to predict convective flux and tendencies based on the grid scale, temperature, and moisture. This is a very simple schematic. So as an input of the neural network, you have the temperature and moisture profiles. And you have a series of outputs which represent specific processes that drive the moisture and temperature tendencies due to convection. The way we implemented it in CAM was to retain the neural network as we trained it on SAM and regrid the CAM inputs into the SAM vertical grid, essentially, run the neural network forward, and then grid the SAM-like output from the neural network onto the CAM grid. This allows us to retain the weights that we've computed with using the SAM data and hence not have to retrain the model every time we have to change the vertical resolution of the model. We implemented this scheme by replacing the Zhang-McFarlane convection scheme, which is the traditional scheme used in CAM6, but keeping all other schemes active. We also were very careful at making sure that we only presented subgrid scale processes linked to convection. And also we made sure that convection occurred only when we diagnosed a vertical extent of convection that is deep enough to really be significant. We tested this convection scheme in 3 configurations of CAM, which I will show you today. First is a single column CAM, the SCAM model, forced by the Toga core forcings. Then we'll move up into an aquaplanet run, and we'll end up with some results on using the full CAM land ocean. I have to also to mention that we train our neural network on an aquaplanet configuration of SAM, and hence the current version of the neural network is only applicable over ocean regions. So later we will adapt this scheme to include land, but today's presentation will be showing you results on the convection scheme only applicable to ocean regions. What we want to achieve here is to improve or resolve climatological biases, or at least you don't want to make things worse compared to your traditional scheme, and also address well-known biases in precipitation intensity distribution, in diurnal cycles, and also hopefully improve aspects of the synoptic to subseasonal timescales, in particular tropical waves. So the metric here is to do a better job than using Zhang-McFarlane with CAM with a similar to lesser computational cost. So this is the run based on the SCAM model. As you can see, the left panel shows the precipitation over a 22-day time period. And there are 3 lines here. The blue line is the observed rainfall from the Toga campaign at a very specific site in the Western Pacific. The red is using the SCAM model forced by the large scale of the Toga campaign using the Zhang-McFarlane convection scheme. And the green line shows the YOG scheme, which is the name that we've given to our neural network scheme. And as you can see, we're doing a comparatively good or bad job compared to observation as ZM. So we're, I think, doing the implementation of our scheme into the SCAM model is reasonable. There are suggestions to say that we're actually doing somewhat better than ZM in certain aspects. So for instance, if you look at the right panel, it shows the time in relative humidity versus level. And as you can see, one issue with the Zhang-McFarlane convection scheme is that it tends to oversaturate, meaning the relative humidity tends to be too high. When we implement our neural network scheme, our relative humidity tends to be a little lower and perhaps more in line with what it should be when looking at observations. We now move up to the aquaplanet runs. So the left panel shows the total precipitation distribution versus latitude from the south to the North Pole. As you can see, you have your storm tracks around 45-degree north and south, and also you have your large precipitation maximum in the ITCZ. And as you can see, we're doing a comparably good job compared to ZM. There is suggestions that we precipitating a little more than ZM, but overall, we are able to port this neural network into CAM6 aquaplanet. It is stable and it gives us reasonable climatology. I'm also showing you the relative humidity, which shows pretty reasonable relative humidity distribution with your dry zones around 30-degree latitude in both hemisphere and more humid areas toward the mid-latitudes and polar region. The cloud distribution also is comparable with ZM. So far, I think I'm able to show you here that we're doing a decent job. Where I think we improve things significantly is in the precipitation distribution frequency. This is the y-axis of this figure is the frequency distribution of precipitation versus precipitation rate. And you already heard in previous talks about the drizzle problem. So you can see that compared to observation, which is the blue line, the Zhang-Markfarlane version of CAM6 tends to have too much low frequency, low magnitude precipitation. So that's your drizzle problem. And while the extremes tends to be not as strong as they should be in their frequency. You can see that the Yock scheme improved things substantially. It reduced your drizzle, and also it gives you more extreme rainfall events, more in line with observation, although perhaps here we've done it a little too much, but it is, I think, closer to observation overall. So that's a good sign. Now, for the last part of the talk, I'm going to show you briefly our full CAM6 simulation. So what we've done here is that we've turned off our convection scheme over land since it is not applicable to land regions. So we're running the full CAM with our convection scheme over the ocean, no convection scheme over land, and we're comparing that with your traditional scheme on over both land and ocean. This is the precipitation distribution over the ocean. Broadly speaking, it looks reasonable. You can see, however, that we tend to predict too much precipitation, a little bit too much precipitation over the deep tropics and some subtropical regions. Now, if you do a zonal mean over ocean regions only, you can look at the precipitation. So the green line is our CAM6 with our neural network. Red line is the Zhang-Markfarlane CAM6. And then I have also showing you GPCP in magenta and ERA5. You can see that we're definitely over precipitating over the subtropics, let's say, but also we're doing not too bad of a job in the mid-latitudes, polar region. So there is work still to be done to resolve this issue of over precipitation. But what's promising here, I think, is that the statistics, like for the aquaplanet, is improved. So you can see that we have less drizzle problem. When you look at the right panel, we have less of a drizzle problem and greater amount of extreme events, which I think is more in line with observation. So in summary, we've tested a deep neural network convection scheme and implemented it in CAM6 in 3 different configurations. And we found that it does reasonably well, but there are still some issues that we need to address. What we'll do is in the next few months will be to think about how to lessen this over precipitation bias that we see in the tropics. Also evaluate whether we're really improving things on shorter time scale, like diurnal to seasonal. And at last, but most importantly, perhaps, will be to make it active over land. And this is work that is currently done with Griffin at MIT. Thank you, and let me know if you have any questions.
Just on the last plot that you showed, I mean, it's a significant increase in precip compared to the base case. And I'm wondering, is there anything happening in the near surface that is, you know, you have to have much higher latent heat flux as well to kind of accommodate that. And I'm wondering, if I remember from your single column plots, there was quite a bit of drying near the surface.
Yes, so that's a very good question. We're not fully sure about the source of this over precipitation, but it is linked, we think, to a bias that we see in our cloud cover. So we tend to have two little clouds with our new scheme, and so that indeed drives more evaporation and more rainfall. And our preliminary analysis suggests that it's mostly ice clouds that tend to be prismatic. So yeah.
Great, thank you, Zabe. Oh, sure.
Question makes sense. So convection scheme moves stuff around basically, and then you generate the tendencies. So it's sort of inherently conserving moisture and heat and those kind of things that we need. Is that a property that just drops out of this neural learning, or is that something you have to force in?
So yes, we do. We were careful about that actually, and our neural network does conserve heat and water, and it is done so by predicting the vertical fluxes, specifically of moisture and temperature, instead of the tendencies themselves. And like that, you can, when integrated vertically, fluxes being zero at the top and lower boundaries, you will conserve your energy and moisture. So overall, we do conserve water and energy. Yeah.
We are going to move on now to our next speaker, Jio Wei.
Hi everyone, my name is Jia Hui. I'm currently a postdoc at Brittle Aeronautic University. Thank you for providing this opportunity to present our work today. So I will be presenting an AI foundation model named ChemNet for whole atmosphere, thermosphere, and ionosphere predictions. And here I would like to thanks to my advisors, Wenjun Dong and Alan Liu. So before should I? Top button? Yeah, move to the next slide. Yeah. Oh, big middle. Gotcha. Thank you. So before I get into the details of the model, I would like to introduce the fundamental driving force of this development. So our research focus is the gravity waves. As some people probably not know about the gravity waves, if you can imagine a stone being thrown into water and the wave of the water just propagate outwards, this is similarly to the atmospheric gravity waves. From the Earth's surface, the mountain waves and the volcanoes and the thunderstorm will generate some disturbance, and it will carry the momentum and energy to propagate to upper atmospheres. And the waves will be modulating the thermosphere dynamics as well as the ionospheric, causing the disturbance. So it's quite essential to know the small-scale gravity waves. So some of the high resolutions can definitely help to predict those motions, but the limits is it needs the high computational cost, and it takes excessive time to make those predictions. So that's where the AI-based model comes in. We like to develop the AI-based model to quickly to predict the atmospheric dynamics. Of course, the training process takes highly computational cost, but once it's being trained, it can generate the prediction in a very fast manner. So right now, let's dive into more details about the AI foundation models. So the best way to think about it is to connect the ChatGPT, which is a very popular large language model. So it is being trained on vast data, including the audios, text, and the pictures, and it can be doing the downstream task based on user need. So you can probably send the ChatGPT a code package, and it will use the learned informations and to output the information you wanted. So extending these applications to the weather forecasting side, we like to use the AI foundation models to predict the atmospheric behaviors. There are many of the models out there, such as the GrabCast, the Climax, and the Pangu, and the ForecastNet. Those models are based on different neuron architectures, such as graph neural networks and the vision transformers based on the visual informations. Here I would like to highlight the Fourier neural operators, which training the inputs in the frequency space. The available training data set would be including very popular the ERA5 data and the Mary version 2 data. So I will be highlighting the Fourier neural operator in the last slides is because we are using extension of the Fourier neural operator, the spherical Fourier neural operator here in our model. So the spherical Fourier neural operators are specifically for, it respects the geometry of the Earth, and it is transforming the physical variables into the frequency space using the spherical harmonics compared to the faster Fourier transformation in the FNO. So the spherical neural operator has been, there are some code packages developed by NVIDIA, and the mathematical theories are published in Bonovo papers in 2023. So the most advantage of the spherical FNO is it has a long-term predictability in the in the weather forecasting. As you could see, the animation on the right bottom side, NVIDIA did a study to compare the AFNO and SFNO. So as the prediction time progress, the AFNO will accumulate a lot of errors, and the model will crash eventually after 10 days of predictions. But the SFNO will possess the stability and to predict the wind patterns. So it has a big advantage of the longer predictability. Also, it is more efficient at is using the L filters compared to the L square. So it's more computational efficient as well. And also the SFNO can be generalized to new resolutions as compared to the AFNO has to be fixed grid resolutions. So the reason I compare AFNO and the SFNO because we, before Dr. Dong has already built the ChemNet based on AFNO, and it's being published in the paper of 2023. So in his paper, he simulated the nonlinear atmospheric gravity wave dynamics using AFNO. And this model is being trained by the CGChem model. So it's a very high resolution model. And here in this work, we substitute the training data with the specified dynamics of YCAMX in the CSM community. And then we substitute the AFNO structure with SFO. And also, besides that, the other change is we put the inputs into the small and the large scales to resolve the issues of spectral loss, spectral bias, which is a common issues in machine learning that the machine learning trying to get rid of the small scales learning. So we tried that in our model also. We couple the backbone model of SNO training with the tracer variable predictions. So we get the training weight of the backbone model of the atmospheric variables, such as wind, temperatures, and the vertical winds. And then we get the tracer variables, such as dioxide and neutral oxygen. We got those features and concatenate them together to do the tracer predictions. So to be noted here, for the tracer prediction, we're just using less layers to train, so it's faster and just less computational cost. So, so here, so as we now know, we are using the data from the specified SD YCAMX data set. Here, let me introduce a little bit about the YCAMX data in the CSM community, which is an extension of the CAM, which is a block in the CAM part, and it can simulate the atmospheric variables from the Earth's surface to 700 kilometers. And the reason it's called specified dynamics is because it's not the more realistic data from the MERA version 2 data. So it constrains the lower atmosphere up to 50 kilometers, so it will have more realistic information in this type of data sets. So these data sets used in training, we have the resolutions, horizontal resolutions of 0.9 times 1.25 degrees, and the verticals is variant from 1 kilometer to 50 kilometers. To be noted here, the data we used to train this model, we didn't use the full vertical profile, we just take every 5 of vertical resolutions. And the time resolution is 3 hours. For the data partition part, we use 10 years of data into the training process. And during the testing of the model when calculation, we use 2 years. And for the inference part, which we just using 1 year for validation purpose. So here is the flow chart of the whole model. Given the time, I probably could not get every detail into this, but the key development is so the scale separations, also the change of the frames, and also I would like to mention the other important step is we use 2 stages for training as well. So for the first stage, we just train 1 time ahead and calculate the loss and update the weights based on the loss. But on stage 2, in the fine-tuning process, we calculate 2 times or even more training steps to calculate the sum of the loss and update the weights. So by using the stage 2, it is expected the model could learn more longer time of structures. So after we train the backbone data, we couple with the tracer fine-tuning approach. We also get the tracer variables from the SD YCAMX, and then we feed into the encoder to get the features, also concatenated with the features from the backbone model. And then we use less layers of the SFNO and to fine-tune the data to get the tracer variables. So this is the tracer variable part. As for the result, so here is the inference result. Inference means we use the validation data set of 1 year, which the model never seen before. So we predict the variables of the zonal wind, meridional wind, vertical wind, and the temperatures. So on the left-hand side, it is the animation of 18 epochs. As you can see, for most of structures, they align pretty well. And also, I zoom in views to give some details at the height informations, which we mostly interested in is the 90 kilometers height of the meridional wind. So, and every column of the result is showing between 2 epochs. So, because our time resolution is 3 hours, so the top row is the target, the second row is the prediction in small scales, and the bottom 2 are in the large scales, and the last row is the arrows. So, so the large scales align pretty well. For the top rows, as you can see, the target still has quite some of the small scales that cannot be resolved by the models, but there are still some small scale waves resolved being there, as you spot on the second row here. So to get more statistic analysis, we also did the energy spectral analysis compared at different height. Top row is compared at 20 and the 90 kilometers and the 250 kilometers. So the X bar shows the frequency, and the Y bar shows the normalized spectral energy. So the larger frequency will associate it with more frequent wave or small scale waves. As you probably can see, the alignment for the large scale aligns pretty well, but for the small scales, there's still some deviations, especially at the height of 90 kilometers. The reason we think that is because 90 kilometers, there's a lot of small scale waves out there, so the model will treat the small scales as noise and filter out those noise and not capturing the structures. So from this work, we have tried the ChemNet to predict the whole atmosphere. It has good alignments with large scale and also, but slightly off on the 90 kilometers, and it is compute really fast than the traditional model run. So approximately 5 days training for 10 years of data, and it lasts 12 hours for simulating the 1 year data once after we train the model. So the next step, probably the most important thing, is to resolve the small scale, as we want to study more variations of atmosphere. So we will be trying to use the diffusion model, which is also a popular model that tend to not treating the noise as treating the small scale as noise, but will be showing more small variations. So, and also we're going to couple the physics in the loss functions to make the machine learning model not just only based on the numerical calculations of the MSE loss, but also showing some deep insights of physical loss. So that's how I'll propose the next step. So here's the reference, and thank you for your time. Let me know if you have any questions. Thank you.
Impressive results.
Thank you.
I was curious about the tracer part. So what tracers are you learning? Are those the major species of dry air, or?
Oh yeah, we currently we're trying to use the tracer variables of dioxide and the nitrogen oxide. So we are feeding those data into our model.
Because the most expensive part, since Bill mentioned dicores and any application with aerosols in chemistry, is tracer advection, so that would be very nice to machine learn that to speed up the model.
Yeah, thank you.
Very much. In the past, a lot of the emulators had problems with emulating stratospheric dynamics, and I was wondering if you have some insights why your model or your emulator is doing so well in the stratosphere and upper atmosphere. Thank you.
Oh, for the, sorry, so you mentioned why emulator is doing better in stratosphere and the ionosphere?
In yours, yeah.
Oh, I see. So I cannot say the results since we didn't do a comparison study. We just did the model to compare to the truth, to the ground truth, which is the SD WAC-MX. But it would be very interesting to compare the emulator with the AI foundation model to see what's the gap there and to see how could we further improve our model. Yeah, thank you.
Nice talk. So my personal feeling with ForecastNet is that it lacks of the seasonal cycle. So I want to know if you have better results in your emulator.
For the FNO, based on FNO forecast?
No, Sapphire for Sapphire for neural operators. Version 2, ForecastNet version 2. The seasonal cycle is not that great.
Yeah. So you mean if you've seen this slide,
days or 20 days round. So if you run for 365
more days,
years,
yeah.
So it lacks of seasonal cycle.
Yes, so I think that's one way to improve the predictability, as is also an issue in the models. I think currently we are trying to extend the prediction to maybe just a couple days to a month, but I think there's still some improvements to do that. And the reason that we update with the AFNO with SMVol is also for the long-term predictions. So I think. Thank you.
Okay, we're going to move on to our next speaker. This is Iris.
Yeah, hi. I'm standing in for Mengze, who couldn't be here. This is really mostly his work, and I hope that I represented well. So the title is Generating Large Ensembles of Precipitation Extremes from CESM Simulations Using Score-Based Diffusion Models. Both Mengze and I are part of a project at MIT called BC3, which means bringing computation to the climate challenge, and the goal of this project really is to use emulators to democratize access to climate data. So I wasn't here in the morning, so I don't know how much like general emulator contextualization has been done. But I think the word emulators is used for many different things, and I just wanted to sort of put into context what type of emulator we are talking about in BC3 mostly, or at least in this talk. So this is a flowchart from a preprint by Claudia, who is also an external collaborator in our project. And this sort of shows, I guess, the whole world, right? If we want to model the whole world, then we would have human activities that influence emissions, that then influence the climate and impacts and risk, which then feed back into political and social processes, which change, again, how we emit, etc. And modeling all of this is, of course, a very big effort. And the climate part of things, so that's the green arrows in this flowchart, can do only that many possible scenarios, both social scenarios, but also just emission scenarios, right? Like that would be the SSPs or the RCPs. So the emulators that we are talking about in BC3 mostly are emulators that can maybe replace or fill in part of these arrows, albeit dependent on models that have been run. So model data is needed to train these emulators, but they can maybe replace some of these arrows to then represent a larger magnitude of possible futures or outcomes or realities, and maybe also model some things that we have a hard time modeling physically, so really like data-driven emulators. And in this talk, I'm really focusing on the smallest green arrow. I don't know where the pointer is here. The smallest green arrow that really goes from concentrations or radiative forcing towards impact-relevant climate variables, or sort of the output climate variables that climate models also produce. So most of the emulators that have done this little green arrow, so going from emissions to climate variables, are, maybe I'm misrepresenting it a little bit, but at least until a few years ago, these really used to be mostly pattern scaling emulators or sort of mean state emulators. So going from one-dimensional time series to patterns. But of course, in reality, most of the things that are socially relevant, climate impacts that are relevant, are not necessarily related to the mean only, but also really need to take into account natural variability and, for example, extremes. So what we are trying to do is to emulate the distribution of climate variables so that we can say something about the mean, but also about extremes, frequencies, intensities, and how these might change in time, and also how they might look in scenarios that we have not run with our full CMIP ensemble. So that's really going from this mean Q or mean quantity to a probability of Q given a certain climate state. So in this case, it's global temperature. The emulator that we use, or that Mengze and Andre Souza developed for this, and this is not my expertise, so bear with me here, is a score-based diffusion model. So I guess the process that we sort of went through in this project was to go from emulating distributions with more like normal Gaussian type emulators, which works quite well for mean temperature variables, but then as we wanted to go to more nonlinear types variables, such as daily precipitation, we obviously needed more flexibility in what kind of distributions the emulators could produce. And so we ended up with these score-based diffusion models for now, which work by iteratively adding noise to a snapshot of precipitation, to the variable of interest. And then so this is really not my expertise. The machine learning aspect then learns how to go back from the noise to the initial input, which is climate model data. And in that process, we generate this reverse diffusion process that then can generate the variable of interest from plain noise, so from random stochastic noise, which allows us to basically generate, if you like, infinite ensembles of the variable that we trained the model on. So we applied this procedure to CESM mesaclip data. We only did it for the low resolution now, but we started using the mesaclip ensemble because that would also then maybe enable us to go to the higher resolution ensemble and emulate that, which is arguably even harder for the emulator given the smaller scales and the higher variability, but potentially also more useful given the goal of emulating extreme precipitation in a larger ensemble and maybe for different scenarios. So we trained the emulator on daily precipitation June, July, August, and only on one member, mostly for computation limitation reasons. So we trained it on one member, and then we generated as much data as the full ensemble. So we generated 10 members of daily precipitation. And the evaluation that I will show you now of the performance of our emulator focuses on the extremes. So we've emulated daily precipitation, and then I extracted the yearly or the seasonal extreme, so the daily maximum in every year of emulation and also in every year of reference data. And then we ask, can our emulator produce this most extreme, basically most far out tail of the climate distribution? And I guess there are two questions that I'll focus on in the remainder of this talk, and one is whether the statistics of precipitation extremes are well reproduced by the emulator. And the second is, if we zoom in on individual extremes, does the map also look, so the spatial pattern, does that also look representative? Because it's of course also relevant from a impact point of view. So first, let's look at I'm just checking the time, at the statistics of the extremes. So these are maps of generalized extreme value distribution parameters. Those of you who've heard me talk before know that I like GVs. The top row shows the location parameter, so that's sort of like the mean of the distribution of extremes. The middle row shows the spread, and then the bottom row shows the shape, which is about tail property. So really this bottom row shows most non-Gaussian aspects in it, and also shows that our emulator can in fact produce non-Gaussian distributions. What we see is that the general maps look quite similar in a general point of view, but if we look at the difference maps in the rightmost column, so emulator minus the reference data or the training data, then we see that the differences are really quite large. So all the color bars are 10% of the total color bars. So those are really quite big errors, you could say, or biases, which are probably still also quite tunable because this is a quite preliminary version of the model for the CSM data. But we do see some structure also that's interpretable in the differences. Mostly it's smoothed gradients. So wherever the reference data is dry, the emulator is a bit too wet. Where the reference data is very wet, the emulator is too dry. And this is in line with the emulator type that we use. So with the score-based diffusion model, it's not uncommon that you would see such sort of smoothing effects in the emulator output. Yeah, this is a similar plot, but if we look at more impact-relevant variables, so the 20-year return level of precipitation, sort of taking together not these statistical parameters, but taking like an actual output impact, then we see similar things. So general gist is the same. The pattern looks relatively similar, but the differences are sort of lower gradients, smaller gradients in the emulator compared to the reference data. Then I hope that this looks okay. Then if we look at these physical characteristics of individual events, so I chose 3 regions, Brisbane, Boston, and Mexico City, and for both the emulator and the reference data, I selected 3 top 10 precipitation events in those cities, and just plotted here the day, so the way the precipitation pattern looks on that day of maximum precipitation. And as you can see, they're all different because they're different events, but we do see features that are similar. So the emulator produces features that seem to correspond to what the actual model also produces, especially here in Mexico City. You see very clearly this atmospheric river, if you like, that then comes from the west and hits the coast. And it's cool that we can see that those features are also represented on a daily scale in the emulator. And if we look at the composite of the 10 most extreme events, these also look similar. Of course, they're not so surprising. It's just a blob of rain around the city, but you see some structure that suggests that the meteorological features are comparable. So that's already the end. So we see that these score-based diffusion models do reasonably well at capturing nonlinear climate variables and also the spatial characteristics of individual extremes. I put an asterisk there because there's still some tuning to do for the model to really say, okay, now we can use it as an emulator for extreme precipitation, because the biases that I showed today were still too large to say that. And I think what's really next steps, like in this whole process of emulating extremes or impact-relevant climate variables, is to go more into this scenario interpolation. So this was all just dependent on global mean surface temperature, which is a very coarse representation of a scenario, right? It doesn't give you that much more flexibility. So I think including more predictors that really increase the scenario space that we can emulate is a priority for these types of efforts. And then also, of course, extrapolation. If we talk about large samples, it would make sense if those samples also included events that weren't in the training data, because then we can actually learn something new. Thank you.
So thanks for using our Mr. data sets. So I'm a little bit puzzling about your training strategy. So what's your input variable?
The input variable is daily precipitation, June, July, August. So it's daily fields of
precipitation.
Output as well. So the input and the output are so the covariate is global mean surface temperature. And it's trained on daily precipitation, and then it also outputs daily precipitation. So it's a stochastic model that generates plausible representative precipitation fields as a function of global mean surface temperature.
Just using a precip to emulate the extreme precip.
Yes, because the daily precipitation, so it's daily precipitation the whole distribution is generated, and then in the post-processing, I extract the extreme precipitation from the emulator. So we emulate daily precipitation. And I now showed an evaluation of the extremes in the daily precipitation sample that is emulated.
Thank you.
Okay, we're going to move on to our next speaker, which is now DJ.
All right, good morning, everyone. So today I'm going to talk about our Community Research Earth Digital Intelligence Twin, or CREDIT, which is our new AI weather to climate and whatever scale in between AI model emulator framework that we've been developing at NCAR for the past couple of years. This has been a huge joint effort among a lot of people here. So I know a few of you are in the audience, so if you've been involved with CREDIT, can you stand up real fast? Yeah, so I want to thank them and a lot of other folks here for their efforts, and please go talk to all of us during the discussion and during the lunch break today. So why did we develop CREDIT or why did we decide to go down the path of developing CREDIT? As people have been following in the news, but maybe going back a little bit further than that, a lot of AI weather and climate work was focused on kind of a lot of sort of single variable kind of problems, more post-processing. A little bit of parameterization was happening back in 2018, 2019. But a few folks were bold enough to think maybe we can emulate the entire model. And so basically the weather bench data set was developed, and like it came out at the same time as Error 5. We saw a number of groups starting with kind of individual grad students, and then growing to large tech company efforts like at NVIDIA and Google and Huawei. We saw steady improvements to the point where eventually, in terms of individual variables, we saw Pengu and GraphCast outperforming the ECMWF model on single variables. This led to an explosion of other groups jumping into the fray and trying their own approaches. What we haven't seen with this, like tons of other groups trying lots of different modeling approaches, is that performance has kind of leveled off. There's been some marginal improvements in different aspects, but we're not really seeing, I would say, like that continued upward trajectory. And so it's possible that the scale of the models and the scale of the data, I mean, it's possible that that's one of the limiting factors, but I think one of the other issues is not getting the physics entirely correct. So there was a study by Slavinsky et al. Kind of down the road from us at NOAA that ran a number of these models with basically assimilating surface pressure and doing cycle data assimilation, kind of like you would with the traditional NWP model. And the problem they ran into is that eventually all of these models would go numerically unstable after a certain point, except for deterministic neural GCM, which is a hybrid model. And none of them outperformed the UFS in kind of this more realistic setting. So this is telling us that while, like in terms of global skill scores, we're getting good performance, there's some other inherent issues in how the models are propagating data around that need to be addressed before we can really, say, want to deploy these in all kinds of different applications. And to solve this problem, I think it's not just like kind of come up with a new architecture sort of problem. It's really thinking through the data, the models, and the physics. And so in order to do this, and to help the community do this, because after all, we're at the CESM workshop, and the community is kind of the key part of this and a key part of NCAR. We developed CREDIT, which is, we call it an open foundational platform. So rather than a foundational model, we have a foundational platform that you can use to develop and deploy AI weather and Earth system prediction models. We've added kind of a pipeline to handle different data sets. We started with Error 5, we brought in CAM, we brought in CONUS 404, we're starting to bring in GFS, and we're looking at other models or other data sets already. And then we've implemented multiple modeling frameworks. Some we've adapted from other groups, others we've kind of cooked up ourselves. And then we've added ways to conserve physics, at least at the global scale for now, but kind of in a more modular framework to enable mixing and matching all of these different pieces. We have some scientifically validated cases, but we also want the whole community to be involved in trying this out and running this on your own use cases, not just in the atmosphere where we're starting, but thinking about the ocean, the land, the ice, and how these all interconnect. So the basic components of this is first we have to process our input data into AI-friendly chunks. This turns out to be a very important thing for not breaking the supercomputer, which we did a few times in the training process. In terms of our variable types, we support kind of prognostic or input and output variables, static and dynamic forcing, which are input only, diagnostic variables that are output only, and then we can do derived variables and interpolate on pressure and height levels. To train your model, you start with creating a PyTorch data set that loads in your data from disk. You run it through a transform to normalize or otherwise rescale your data, feed it through your model, feed it through what we call post blocks that apply physics corrections, and then you calculate your loss and then update your weights using backpropagation. You do this until you get decent convergence, and then maybe you want to run it out further in time and learn from a longer range trajectory. So we support multi-step training where you basically do the same thing, except the difference is now you have to cycle your model a few times and then take the loss over that trajectory. And we have some ways to scale this on the supercomputer so that you're not basically balancing that memory and computation challenge. And finally, we have prediction, where we actually want to launch our model and new data hasn't seen, and we can run it forward. And then we can do post-processing on that and calculate both metrics and outputs and save it all as CF compliant .NET files that you can then feed into all of your favorite diagnostic packages. Our first version of credit focused around a model we call WEXFormer. For this, we took ERA5, but instead of using pressure levels, we used hybrid sigma pressure level data on a 0.28 degree Gaussian grid, so the native grid of ERA5 plus filling in to a full Gaussian instead of reduced Gaussian for those who care about those details. We like kind of use different years for training, validation, and testing in line with a lot of the weather bench models. In addition to kind of our prognostic variables, we have some forcing variables, and then we also output, use as prognostic some 500 millibar and surface variables to allow us to more easily diagnose how well the model is doing without having to do all the pressure interpolation every single time. In terms of our model architecture, it's not I would say not particularly complex or revolutionary. We use some short and long range attention in the encoder part of it, and then we have standard convolutions for the decoder part, and in between we have basically send data across. So it's basically a UNet architecture. Nothing fairly like revolutionary in that part. The revolutionary part, though, was a discovery that John Schreck made that you could use spectral normalization, which is a trick from the GAN community, where you rescale your weights during, basically, when you update your weights, you take the spectral norm, which involves sort of a singular value decomposition. And when you do this, you rescale the weights by the first principal component effectively. And this helps prevent both exploding and vanishing gradients, and we found it generally improves model stability. So a lot of other groups, so like Pengu, Fuxi, Fengwu, all have like these cascading models where they switch to a different model a certain number of steps into the process because their model is blowing up or getting too smooth. We don't have to do that. And we can also run at arbitrary time steps. We have a 1 hour model and a 6 hour model, and both can run out quite long and don't go unstable. There's still artifacts, so it's not perfect, but we've applied this both to WEXFormer and to Fuxi, and we're seeing similar results. In terms of our overall verification, I picked a number of the 500 millibar and surface fields to kind of show as an example. The blue line is ECMWF, IFS. The green line is Pengu, and WEXFormer is the red line, and Fuxi is the yellow line. We also have our 1 hour WEXFormers on there. It's like kind of the maroon line. What we're generally seeing is that our 6 hour models generally outperform IFS and are competitive with Pengu with some slight improvements at longer lead times. We're also seeing the 1 hour model is competitive and maybe a little worse, about the same as IFS, but it's stable out to that long range, and no one else has been able to pull that off to this point. In terms of our kinetic energy spectra, like a lot of these other systems, we're over smoothing the data at the fine scales. And there's a few like wave artifacts we're seeing that also show up as little spikes in the data, and seem to be more prominent once you get out to like 10 days in the 1 hour model, but also show up in all the other models too. So not a unique problem for us. In terms of what this looks like across different vertical levels, so we are generally pretty sharp in the lower atmosphere, but as you go higher in the atmosphere, especially once you get above the tropopause, we start smoothing things out quite a bit. We capture some of the very large scale waves in the stratosphere, but a lot of the smaller scale gravity waves aren't showing up. And so that's something where there's certainly room for further improvement, and we're kind of thinking about ways to do that, and interested to see what the previous talk focusing on the stratosphere learned from that. So this was our first go at it. Didn't have any physics conservation built into it. So Kyle Shaw, who was a postdoc with our group and is now a project scientist in the Research Applications Lab, decided, hey, what kind of physics conservation can we put in? How does that affect the model? So we took a 1 degree version of it, created a 1 degree version of Era 5, added precip, evaporation, radiation fields. Also, sea ice cover was turned out to be really important for surface temperature, and some other information about the land surface. And then trained a version of the Fuxi model, which the architecture is shown up here. It's a variation of what's called a Swin transformer. And then we added some kind of model agnostic blocks that basically don't have any trainable parameters, but just run a conservation based off of the initial conditions of the model. So first we do a non-negative correction to get rid of any negative precip or humidity. Global dry air mass conservation to fix the dry air mass budget, moisture budget conservation, which adjusts the precipitation evaporation, and then total atmospheric energy, which adjusts the temperature. We do like a multiplicative adjustment to these fields globally, so nothing is moved around. We just like kind of multiplicatively scale everything based off of the ratio of like the initial conditions and current conditions. We do this during both training and inference, which turns out to be important. I'll show in a second. And then from there, what we see is so one thing that has come up in the discussion is you're only as good as your training data. Well, it turns out if you add physics, you can actually fix things about your training data. So IFS and Era 5 have issues with what's called drizzle bias, and if you train with it, you actually get an even worse drizzle bias. But if you add the physics correction on the non-negative correction plus the moisture budget correction, we get rid of the drizzle bias. So if you look at Antarctica and at the Sahara in particular, you see it's a lot whiter. There's none of that pink that you see in the other fields. We also see improvement, and this improves our precip scores overall. We don't sacrifice performance at extremes. We also get better performance in terms of other variables, especially after 4 days, thanks to all the physics corrections. How far does this benefit us? So if we run this out for a whole year, so now we're starting to get into closer to our longer term scales here, we see that we're able to basically conserve the physics in terms of our drier mass, global precipitable water tendency, and atmospheric energy tendency. It's not perfect, but our tendencies are much smaller and much more balanced over the course of the year. Even though Era 5 itself does not balance these things, it is not conserved, we're able to enforce that and get good predictions. We also did some ablation studies. How much do different things affect the model? What we see is if you run it during only inference, all the conservation during only inference, your forecast gets a lot worse because now you're showing it predictions that look a lot different from what it had seen in the training data. Whereas if you do it during both training and inference, you get a much more robust result. The model doesn't have to compensate as much for differences from physics. We see the drier mass has the biggest, mass conservation is the biggest influence, but energy conservation does help a bit on some of the variables. So it's hard to make it a little bit better. It's easy to make it a lot worse. We also show some other physics constrained fields. So we have precip field and total atmosphere net thermal radiation. They're fairly smooth because this is at 1 degree, but we're seeing steady evolution of different fields. We see tropical cyclones in the figure. That's compression from the video, not from the AI algorithm. So it's looking very promising, and Will's going to talk more about the climate side of this. But want to kind of like from a bigger picture perspective, how can we potentially use, or how could you use credit in your research? So if you're a grad student, I think one of the big advantages is one, being able to quickly generate large amounts of model output, and since it's all in Python, you can easily add other diagnostic packages into the flow and run online while you're doing this, and so save out the things you only want to save out, and maybe even do some of the analysis and plot generation with one script rather than having to compile a bunch of Fortran and then kind of have a much longer pipeline. And we can really speed up you can do more iterations potentially of your model runs. If you can do this, like generate your models in a day rather than a month, that kind of changes the way you can spend your research time potentially. Same with if you're thinking about risk modeling, we can look at compound risks much more easily and generate lots of ensemble members. But of course, I think part of this is still we need to validate these that they're doing all the right things before we go completely hog wild with this. So some future directions, we're currently working on ensemble generation. We're testing a few different approaches, some that like everything from diffusion to different kinds of noise injection approaches that kind of, the noise injection seems very promising so far, and we'll hopefully have more to speak about that in a few months. Looking at new model developments, how do you trade off data volume, model size, input data size, physical constraints to get a accurate but also fast model. I think the vertical exchange of information is a very important thing that we need to work on. It seems the models are underdoing it right now pretty consistently. So what can we do on the ML side to address that in terms of how we represent the vertical scales? I think some of this is we just under-resolve the vertical in our current generation of models, and hopefully either add more levels and more explicit attention in the vertical might fix some of that. And then there's, I think, a question of like, this end-to-end approach is much more efficient to train. Component models are more interpretable. What's the balance to strike to get that scientific understanding, but also not have to spend years to do that? So I think it's still a very open question, and I think open to the community to kind of figure out what they want, what works well for their different use cases. We're getting more software engineering support in terms of next steps. Regional model we're training and evaluating right now. It's looking very promising. We're also looking at S2S and longer scale rollout evaluations. We can clearly roll out to S2S scales and do it stably, but is it actually performing well? That's an open question. And we're working on our next generation weather model for the globe and looking at some different data sets that could be promising for that. And so that code's open source. Go check it out. We have our papers online. Our initial credit paper is just accepted to MPJ, Climate and Atmospheric Science, so that'll be coming out soon. It's already on archive if you want to take a look, and we have docs and developers here if you want to ask us lots of questions. So with that, thank you.
Thanks for the overview. This sounds really valuable. Really specific question about introducing the mass fixer. It sounds like a really traditional, like old-time climate modeling approach. Has anyone considered trying to have a learned mass fixer that redistributes the mass in some sort of learnable way?
So Kyle did look into things that were more localized and could redistribute stuff, but it started to get really complex to actually pull this off and add a lot of computation. So he decided to go with the global and call it good. But if anyone wants to try more local approaches, we're certainly open to collaborating.
Okay, we'll move on to our next talk, which is Will Chapman.
Awesome. Yeah, so I am the thing that stands between you and lunch, so we'll try to move this along super quick. So DJ just introduced the credit system, which was developed by a whole bunch of folks in this room. The development really started about 1.5 years ago when John and I locked ourselves in a room and started really hacking away on the code. And then since then, there's been just an unbelievable amount of folks that have joined this effort and really all the work that you see today is building off of a lot of stuff that has been added here in the past. And we're really, really excited about the project, and we really want to treat this like a community platform, very much in the vein of CSM. So if you want to get involved, you saw the folks that stood up before, please come talk to us. We are actively trying to get people to use this system. So you are going to recognize this first slide. To set the context of what DJ just told us, we're going to be talking about one of the data sets that we are currently actively supporting here. So this is the community atmosphere model. And in our development branch, we have now supported much more components within CSM. So we have data sets in machine learning ready format for different parts of POP simulations, CLM, and some of the CIs fields also. So we are actively moving towards a more active model state. I'll also note that, as DJ pointed out, we have capability for our WEX-Former model now to do diffusion-based emulation, which will handle a lot of problems for some of the smoothing fields that we see, though we don't know if that's going to be our ensemble-based system yet. So today we're going to be talking about emulating just this data set here, the community atmosphere model. And the model that we're doing it, you might recognize this figure from what we've just seen. So this is the Camulator architecture, which is very similar to basically uses the WEX-Former backbone. We changed some of the upsampling blocks in our most recent version of that model. We then pushed that through similar physics conservation blocks that you've seen before, slightly adjusted so that we're exactly conserving rather than getting close. And then we then push that through the training loss scheme so that everything is updated based on the forward model run. So what this is a one input, one output kind of system. So we take the current state of the atmosphere, we just predict the next state of the atmosphere. We're not doing tendencies, we're doing that full emulation process. So when we have released one paper on this, or put it out for preprint called the Camulator paper, so this is trained on over 30 years of this observed record forcing, and the throughput of this model is we can get about 480 simulation years per day as we're marching this thing forward. So what is the actual data that we're training on here for this Camulator project? So what we've done is we've created an FHIST run for our version 1.0. So we conduct this 35-year FHIST run from 1979 to 2014 of CAM6 in CSM version 2.1.5. We then collect 6 hourly data. So our time step is a 6 hourly time step. We compute total water and convert to some flux forms so we can ensure that we are conserving energy in and out of the model, and then gather the static and forcing data. And we have our static data here, which is the land surface geopotential height and the land sea mask. We then force the model with solar incoming radiation and observed SSTs. And this is the suite of variables that we are predicting here. So we have prognostic variables, so UVT and Q tote, which is the sum of all the water in the column, and then surface pressure and surface temperature as our prognostic variables. We'll note that we are operating on every model level, so we don't do any vertical coarsening. We felt this was important for some of the reasons that DJ talked about before, how we're losing some information. Additionally, CAM is used for a lot of other things in terms of basically interfacing with other processes broadly in the community. So we want this to be as easy to use as possible. So the output from this model should be easily plug-inable to any process that you're currently either evaluating them on, or say you're doing something like supermodeling where you're connecting model states. You don't have to do any interpolation. We're in the exact model resolution that you see with CSM. Additionally, we have a bunch of diagnostic variables here, including precip, some cloud variables, surface stresses, surface wind speeds, evaporation, things we need to close budgets, and also gives us the ability to couple to some other components of the model as we move forward. So these are the data that we are attempting to emulate. So I got to name this model. So we're emulating CAM, and I called it Camulator. I was told yesterday that was maybe a mistake because now we are trying to do a CL emulator and a momulator and a populator, and it's getting out of hand. So this is the promo video that I made for it. And what we're looking at here is the surface specific humidity, or that Q-tote variable. And really what you can see is it passes the eye test. So we see atmospheric rivers as they're flexing and hitting different west coasts. We see a little bit of a diurnal cycle as it pulses in the tropics. And this will run out for indefinite time periods. We don't see any major model instabilities. We also don't see a lot of the model smoothing that we have observed with our other system, because essentially during the training process, we have ensured that we're not doing long rollouts because we don't care as much about the prediction task, we care more about the generalization task. So the smoothing is not really a huge issue with this modeling system. So I'll show you one more pretty visualization, and this is the precipitation climatology as it develops within our model. So essentially we're averaging precipitation. You'll see the ITCZ develop in the southern ITCZ branch, along with flexing into the Asian monsoon region, development of some atmospheric river fields. So this is a 5-year climatology as it builds, and you can see the nice precipitation fields. So how are we doing in terms of just biases? So we want to be able to ensure that we are representing our CSM 2.1.5 system to the highest fidelity as possible, so that then we can turn around and use this for potentially either model development or some sort of ensemble creation, and trust that it's representing the fields. So these are the biases that we're seeing at present. So we have in purple CAM, in teal camulator, and then I've also put the GPCP product on there on the top left, and that's a zonal mean. You can see it's representing the field fairly well. Camulator has a little bit of, struggles a little bit, especially over Central America is where we see our largest precipitation biases. In terms of temperature, the big error that I can't seem to knock down is over Greenland. So this is sort of my Labrador Sea. I go in every day and try to ensure that this bias goes down, and I'm trying to knock it down and I can't quite do it. I think it's linked to a 2-week NAO right now. So I'm thinking about ways in order to try to encode some more of the low frequency variability into this. Overall, though, these biases are much in line with what you would see with various model tuning runs as you go through the tuning process of a traditional model. And I'll say the epoch-to-epoch variability of the biases is fairly low, but you do see different biases pop up as you run out of epochs. So our training strategy was really to pause at every training example loop, run the model out for a year over our validation suite, and take statistics over that year. The model that minimized sort of the bias in that validation year is the one that we have sort of frozen for now for our version 1.0. So in terms of stability and long-term rollout, on the top, I am forcing the model with historical SSTs, and I have 24 ensemble members. And what we're looking at is the total heat capacity in the atmosphere. In purple, you see CAM6. What you'll notice is some year-to-year interannual variability, particularly around ENSO years. I can say we are a little under-responsive as we move out into the later time period. But importantly, this is a 24-member, 35-year ensemble that we completed in 8 hours on a single GPU. So to do a similar run, this would have taken 4,000 hours of a CAM6 run, or 166 days, giving similar compute. So it's really a step function if we can figure out if we can trust this model, trust the model fidelity. On the bottom, what you're looking at is a 250-year rollout in which we force the model with climatological SSTs. We get a stable rollout. We get a really nice annual cycle, and it runs indefinitely and stably without any major grid artifacts. So what we've done next is a series of tests just to take some first-order approximations at are we getting correct model responses to some different forcing scenarios. So what we've done is we've taken that 2000 year, or year 2000 climatology, added 2K of uniform warming and 4K of uniform warming. And what you're looking at here is 3 different model levels. So on the top panel, you have the lowest model level, or sort of the surface representation of temperature. Middle panel is the 1000 hectopascal to 850 hectopascal integrated heat content. And the bottom panel is the 200 to 850 hectopascal integrated heat content. And in dashed line, that is CAM, and in solid line, that's the cumulator. I'll highlight that these are temperatures that this model has never been anywhere near. So this is well out of distribution. What we would expect is the model to completely freak out. What we see is a stable run, so it doesn't blow up, but we do get a certain amount of biases introduced into the system. So the lowest model level does fairly well, but that model level is driven by SSTs, so you'd expect that to do fairly well. The integrated heating profiles, especially in the lower levels for the 2K heating, is represented fairly accurately. When you get up to the 4K heating, or that green line, you see that definitely during boreal winters, we're witnessing some sort of bias there. So the model is not getting warm enough. And essentially what this is the model has never seen a state where the sea ice is that low or the temperatures are that hot in the Arctic. And I'll point that out here. So these are the biases in the 2K runs and the 4K runs compared to what CAM is doing. You can see that the major biases are really happening in the Arctic regions. And we speculate that adding more sea ice information and getting some more of those physical processes in there will help to improve these biases. And I'll show you some quick results on that in just a second. So that was our version 1.0, and that's the paper out on archive. What we've done since then is we have run a coupled simulation, and now we are training on this model data. And I got these results all just prior to the computer going down, so you're going to see some quick results with a model that is not fully trained yet. But I wanted to show you some fun new stuff. So what we've done is we've taken a coupled run in the CMIP6 suite. We then branch a hybrid run off of it, or we do a hybrid run off of it, run that forward in time to 2014, and then do an SSP 245 foreseen scenario out to 2050. So what we'll do is we will use our pre-trained model from before. We will then switch over and train on the coupled simulation, and then we are going to test the simulation from 2015 to 2050 to see how it responds in a future climate warming scenario. Some things that I've added and switched between version 1 to version 2 is I've added surface temperature as a variable, added some sea ice information, so adding sea ice fraction, CO2 volume mixing ratio, forcing from the coupled oceans, and now we have a coupled ocean rather than an interpolated observed ocean. Remove some redundant variables. For example, we had cloud total, but that was just a sum of the 3 other cloud variables, so I've taken that variable out. And then altered some of the technical aspects of the machine learning layers themselves, particularly the up convolutional layers were causing us some problems, so I've adjusted some of our machine learning suites to improve some of the representations there. So now what you're seeing is 2 runs of Camulator and CAM. Again, we were just trained in that first period, and now we're validating, and this is the total integrated heating from 2000 to 2050. And you can see that for the total integrated heating, even in a sort of a suite of, or an era that Camulator has never seen before, it tracks the integrated heating very, very well. So we are getting that climate change signal in there. So I wanted to run some really quick and dirty tests to see exactly what's being, what really the model is looking out to get this signal. We know that we're forcing it with an SST that has that in there. So I held that SST constant at 2010 and just cranked up the CO2 to see if I could see any weird behavior here. And it turns out we see some massively weird behavior. So as I crank up CO2 and especially get to the end of that period, that's a CO2 level that it's never seen before. And it is, yeah, really going off the rails there. But that does tell us that there is some sensitivity to the CO2 forcing, it's just not the right one. So if you hold CO2 constant and you crank up the SSTs, yeah, it tracks it directly. So it's really just using the sea surface temperature information to get that total integrated heating. So not exactly what we want, but we have some strategies now that we are thinking to start to address some of these problems. So finally, we have, now that I have retrained the model, I forced it again with this 2K simulation, 2K plus SSTs, and I have essentially oriented that top right figure where whenever the colors on top match the colors on bottom, we're improving the biases in this simulation. So did adding the CO2 and adding the sea ice improve our representation of the biases in this 2K simulation? It looks like it did everywhere in the Arctic and over the sea ice regions, but we're sort of getting the opposite response in our Antarctic region. So there's still some work to do there, even for our version 1.1. But what I'll say is we're in active development here. We're treating this like a true modeling project. We want to find the highest fidelity field. So we've passed off these simulations to outside groups to do model evaluation. We're working with Senna to start to do some of the greens function evaluation. And we really want the community to take a good hard look at this, tell us where the biases are, because now we can start to address those things. And it was really encouraging to see the history of CSM talks yesterday and the long sort of model development framework. And I'll point out that the machine learning emulators have been going for 3 years now, really, 2-3 years. And there's been a lot of progress made, but we have a long ways to go. It's really going to be helped if physical modelers can be involved in this loop. Folks that know the systems and the physics really, really well and can start to help us iterate on these biases. So it's so encouraging to see CSM and this community really embrace this, and especially folks from things like the M² Lines project, which, as you mentioned, all of my time is funded from Schmidt Sciences here. So really, I will put up some next steps that you saw from DJ. I'll add that we are currently trying to couple to an active ocean. And working with some of the folks at M² Lines, we're hoping to couple to their ocean emulator here soon. So that's some of the work that is planned in the future. And I'll throw up that last slide that DJ had, and I'll throw my contact there for you. If you want to chat, use the system, please contact us. We really want to test this thing out. Thanks.
We have time for one question.
That's why I just run so hard. Yeah, thanks, Will. So I couldn't find like geopotential height as one of the output variables, and I'll be really interested if you can adapt that for the next versions, because it's such an essential component. So yeah.
Yeah, you can calculate it from the fields that we currently simulate. So we are working on basically an interpolation layer that kind of does that for you. So we'll take out the guesswork for you, and DJ has a nice mod that's already in our toolbox, so you can do those interpolations. It's really fast. It's really, it's slick. So yeah, if you want to talk to him.
Okay, good to know. Thank you.
Okay, great. And before you all leave, I just wanted to put in a plug. We have a CGD machine learning group, and if you're interested in joining to learn about progress that we're making in CSM3 MLE and other machine learning applications using CESM, please let me know. You can come talk to me out during lunch or whatever. Give me your email, and I can add you to the email list. So, all right.